Hello my friends, and welcome back to the You Can Do TV channel. Machining extremely large workpieces is a demanding task that requires specialized expertise and equipment to achieve high precision and accuracy. Simplecamp, a renowned company in this field, is known for its high-precision machining of very large and heavy workpieces using the double shooting technique. Here are some of the key challenges associated with this process. Machine capacity. Dealing with workpieces of colossal size and weight demands machines with substantial capacity and robustness. The machines must have enough power to handle heavy cutting loads while maintaining accuracy throughout the entire machining process. Structural integrity. Maintaining the structural integrity of both the workpiece and the machining equipment is crucial. The cutting forces involved in machining large workpieces can induce vibrations, leading to deflection and affecting the dimensional accuracy of the finished product. Special measures, such as reinforced machine structures, damping systems, and vibration analysis, are required to counteract these effects. Thermal stability. Large workpieces are prone to thermal expansion during machining, which can introduce dimensional inaccuracies. Managing heat generation and dissipation is crucial to maintaining the workpiece's stability and ensuring precise machining. Tooling and fixturing. Designing and fabricating suitable tooling and fixturing solutions for large workpieces is a complex task. The fixtures must securely hold the workpiece in place, allowing for multiple machining operations without compromising precision. Cutting parameters. Selecting appropriate cutting parameters is vital to prevent tool wear, ensure consistent material removal rates, and maintain surface finish. Achieving the right balance between cutting speed, feed rate, and depth of cut is essential for efficient and precise machining. Logistics and handling. Transporting, handling, and positioning extremely large workpieces demand careful planning and specialized equipment. Cranes, lifting machinery, and custom transportation solutions are often required to move these heavy components safely. Chip management. Dealing with the significant volume of chips generated during the machining process becomes challenging. Efficient chip evacuation systems are necessary to prevent chip buildup, tool interference, and potential damage to the workpiece. Despite these challenges, companies like Simplecamp have developed expertise in machining extremely large workpieces with high precision and quality. Their capabilities play a crucial role in various industries, including aerospace, energy, and heavy machinery, enabling the production of critical components that push the boundaries of engineering possibilities. The roughing cycle is the initial stage of material removal, where the cutting tool rapidly eliminates excess material from the workpiece. This process aims to reduce the overall stock material efficiently, preparing the workpiece for subsequent finishing operations. The roughing cycle is characterized by high material removal rates, and it prioritizes speed over surface finish. This cycle significantly shortens machining times, making it an indispensable step in the manufacturing process. Once the roughing cycle is complete, the finishing cycle takes over to achieve precise dimensions, smooth surface finishes, and tight tolerances. Square keyway milling is a milling operation focused on creating a square-shaped groove or keyway within a workpiece. Keyways are essential for shafts, gears, and other mechanical components that require a positive connection with mating parts, such as pulleys or gears. During square keyway milling, the cutting tool advances along the workpiece's axis to produce a keyway with sharp corners and straight sides, ensuring a precise fit for the key. Vertical milling is a fundamental machining process where the cutting tool moves vertically to remove material from a workpiece's surface. This method is versatile and can produce various shapes, slots, and contours on a workpiece. Vertical milling machines come in different types, such as turret mills, bed mills, and knee mills, each offering specific advantages depending on the application. Thread cutting from the center is a threading technique used to create internal threads in a workpiece. This process begins by drilling a center hole in the workpiece, allowing the threading tool to start cutting from the center and move outward. Thread cutting from the center ensures concentric and precise threads, which is crucial for components requiring secure connections, such as nuts and bolts. This heavy milling process used a powerful Waldrich Plano miller with a 110 kilowatts motor to shape a large plate made of high alloy special steel, specifically Impax HH, with a remarkable tensile strength of 1180 N per square millimeter. The milling operation employs a R220.60 8315 cutter with a diameter of 315 millimeters and 12 cutting edges. To ensure efficient and precise milling, the cutter insert used is the R200. Featuring a CVD coating for improved performance and durability. The milling process targets a plate with dimensions of 2000 by 1200 millimeters and involves rough face milling, where the cutter removes excess material to achieve the desired shape. The cutting speeds, VV, are 65 meters per minute, 215 SFM, surface feet per minute. The depth of cut, A, ranges from 10 to 20 millimeters, 4 to 8 inches. The feed rate, F, is set at 0.51 millimeters tooth, 0.020 inch tooth. The table feed rate, V, is 400 millimeters per minute, 15.748 inch per minute. This heavy milling process ensures precise material removal and achieves the desired shape for the large steel plate. Advantages of brass material machining by CNC machine. Excellent machinability. Brass is renowned for its outstanding machinability, making it a preferred material for CNC machining. It is softer and more ductile than many other metals, which translates to smoother and faster machining operations. This characteristic leads to reduced tool wear and increased tool life, ultimately lowering production costs. Dimensional accuracy. CNC machines are capable of extreme precision, ensuring consistent and accurate dimensions in brass parts. This is crucial for industries where tight tolerances are essential, such as aerospace, automotive, and electronics. The repeatability of CNC machining guarantees the uniformity of parts in large production runs. Wide range of applications. CNC machining of brass offers versatility, as it can be employed in various industries and applications. From decorative components in jewelry to complex fittings in plumbing and electrical systems, brass parts cater to a diverse array of uses. Surface finish. Brass exhibits a naturally attractive appearance with its golden hue. CNC machining can enhance the surface finish further, achieving smooth and polished surfaces without the need for additional finishing processes. This feature is advantageous for parts that require aesthetic appeal. Corrosion resistance. Brass possesses excellent corrosion resistance, particularly in comparison to plain steel or iron. This property ensures that components made from brass are well suited for applications where exposure to moisture or harsh environmental conditions is a concern. Thermal conductivity. Brass has relatively high thermal conductivity, making it a suitable choice for heat exchangers and components where heat dissipation is necessary. CNC machining allows for intricate designs in these heat transfer components, optimizing their efficiency. Disadvantages of brass material machining by CNC machine. Material cost. Brass is more expensive than some other metals commonly used in CNC machining, such as aluminum. This higher material cost can impact the overall production expenses, especially for large-scale manufacturing. Machine tool wear. While brass is generally a soft material, certain alloy compositions can still cause accelerated tool wear due to its abrasive tendencies. Cutting tools may need to be replaced more frequently, increasing production downtime and expenses. Machining speed. Despite its excellent machinability, brass may require slightly slower machining speeds than other softer materials. Balancing the need for precision with the desire for faster production can be a challenge, especially for intricate parts. Chip management. Brass produces chips during CNC machining, and proper chip management is essential to ensure uninterrupted and efficient operations. Failure to manage chips effectively can lead to tool damage, reduced surface quality, and machine malfunctions. Work hardening. Brass can work harden during machining, particularly in areas with high tool pressure or inadequate cooling. Work hardening can result in increased cutting forces, tool wear, and a drop in productivity. Environmental concerns. Brass contains zinc, which can present challenges in terms of air pollution and waste management during the machining process. Proper measures and considerations must be taken to address environmental issues. High-performance trochoidal milling by Fresa is a cutting-edge machining technique designed to significantly improve metal removal rates and overall productivity. This innovative method involves using small-diameter end mills with multiple teeth to create smooth, continuous circular tool paths. The tool's engagement with the workpiece is constantly changing, reducing heat buildup and tool wear while maximizing material removal. Fresa's trochoidal milling is characterized by its ability to maintain a consistent chip load and utilize the entire cutting edge effectively. This ensures a more stable and efficient cutting process, resulting in reduced machining times and increased tool life. The method is particularly beneficial in tough materials and complex geometries, making it ideal for aerospace, automotive, and mold-making industries, among others. Guhring's RF100 end mills exemplify the epitome of high-speed machining with their exceptional performance and almost endless tool life. Setting themselves apart from other carbide end mill manufacturers, Guhring takes pride in producing their own carbide rod, which serves as the substrate material for all their carbide end mills. This level of control over the raw material quality and supply translates into longer and highly repeatable tool life, a crucial factor for high-speed machining operations. Guhring's innovative approach to end mill design further enhances their capabilities. They were among the pioneers in introducing a variable helix end mill design, and their dedication to research and development has resulted in one of the largest standard offerings in the industry. The inclusion of Firex, Super A, Nano Firex, and Nano Tialm coatings adds to the overall consistency and quality of their end mills. These coatings are meticulously applied in Guhring's own PVD coating chambers, ensuring top-notch performance and reliability. What sets Guhring apart is not just their manufacturing prowess, but also their commitment to customer satisfaction. They provide in-house regrind services and offer custom carbide end mill modifications, ensuring that their end mills can be tailored to specific machining requirements, thereby maximizing their utility and prolonging their tool life. The CNC Slant Bed Turning Center Lathe is advanced machining tools designed for precision turning operations. The lathe features a slanted bed design, typically set at a 45-degree angle, which offers several advantages. The slant bed design enhances chip flow, improves rigidity, and promotes better operator access to the workpiece, resulting in increased productivity and accuracy. One notable feature is their versatility in accommodating various workpiece lengths. They come in multiple length options, allowing manufacturers to choose the most suitable machine for their specific projects. The construction of CNC slant bed lathes is characterized by robustness and durability. The Mehanite single-piece casting FC350 ensures structural stability, reducing vibrations and enhancing overall machining precision. Heavy-duty boxways provide exceptional support and rigidity during cutting operations, further contributing to the machine's ability to handle demanding workpieces with ease. Moreover, the lathe can be equipped with optional live tool turrets, which enable multi-axis cutting capabilities. The integration of separate motors for disc rotation and tools allows for efficient machining and reduces idle time during tool changes. Additionally, CNC Slant Bed Turning Center Lathe features a heavy-duty tailstock, adding support for longer workpieces and ensuring accurate positioning during machining processes. The Dugard Heavy-Duty Vertical Machining Center 2210B is a robust and high-performance machining tool designed to handle heavy-duty machining tasks with precision and efficiency. The machine has a spacious working envelope with traverse dimensions 2,200 mm in the x-axis, 1,000 mm in the y-axis, and 900 mm in the z-axis. The generous table size measures 2,200 mm by 1,000 mm and can handle a maximum load of 3,000 kilograms, making it capable of accommodating substantial workpieces. The spindle is powered by a potent 15/18.5 kilowatts motor and supports a speed range from 20 to 6,000 revolutions per minute, allowing for versatile cutting capabilities across various materials. The spindle taper is available in both BBT and CAT 50 options, providing flexibility in tooling choices. One of the key features of the Dugard 2210B is its bi-directional twin-arm type auto tool changer with a 24-station capacity, 32 tool option available. This automatic tool changer ensures rapid and seamless tool swaps, minimizing downtime and maximizing productivity. The machine can accommodate tools with a maximum diameter of 110 mm, a maximum length of 300 mm, and a weight of up to 15 kg. The machine's standard equipment includes essential features like a manual pulse generator, spindle oil cooler, cooled ball screws for X, Y, and Z axes, a work light, air gun, wash gun, 232 rupees interface, oil skimmer, and full guarding for operator safety. Moreover, the Dugard 2210B comes with several optional upgrades, such as a choice of controls, a 10,000 revolutions per minute direct drive spindle with a refrigeration unit, a TSC through spindle coolant tank with filter delivering 80 L per minute at 20 bars, a 32-tool ATC system, and various fourth-axis options for enhanced machining capabilities. JSW Steel Limited is a leading steel producer in India that operates a pickling line tandem cold mill to produce cold-rolled coils. The mill was supplied by SMS Group, a leading engineering and plant construction company in the steel and non-ferrous metals industry. In this video, we will discuss the mill and how it works. The pickling line tandem cold mill is a type of rolling mill that is used to produce cold-rolled coils. The process involves three main stages: pickling, cold rolling, and annealing. The pickling stage involves removing the oxide layer from the surface of the hot-rolled coils. This is done by soaking the coils in an acid bath, typically a mixture of hydrochloric acid and water. Once the oxide layer is removed, the coils are rinsed with water and then dried. In the cold rolling stage, the pickled coils are fed into the mill, where they are reduced in thickness to the desired final gauge. The mill is a multi-stand mill, which means that the coils pass through several pairs of rolls in succession, with each pair of rolls reducing the thickness of the coil by a certain amount. The rolls in the pickling line tandem cold mill are made of high chromium steel, which is highly wear resistant and can withstand the high pressures and forces involved in the cold rolling process. After the cold rolling stage, the coils are annealed to improve their mechanical properties. Annealing involves heating the coils to a specific temperature, holding them at that temperature for a set period of time, and then cooling them slowly. This process relieves the internal stresses that build up during cold rolling and improves the ductility and formability of the steel. This mill was supplied by SMS Group and has a capacity of 1.8 million tons per year. It has several features that make it a highly efficient and reliable mill. One of the key features of the mill is its fully automated operation. The mill is equipped with state-of-the-art automation and control systems that monitor and control all aspects of the rolling process, from the entry of the coils into the mill to the final packaging of the finished coils. This automation helps to ensure consistent product quality and reduces the risk of human error. Another feature of the pickling line tandem cold mill is its high degree of flexibility. The mill can produce a wide range of cold-rolled products, including high-strength steels, advanced high-strength steels, and dual-phase steels. This flexibility is achieved through the use of advanced rolling strategies, such as shifting the work rolls and adjusting the roll gap, which allow the mill to adapt to changing product requirements. The mill is also equipped with advanced quality control systems that monitor the thickness, flatness, and surface quality of the coils in real time. This allows the mill operators to make adjustments to the rolling process as needed to ensure that the finished coils meet the customer's specifications. In addition, the pickling line tandem cold mill is designed for high productivity and uptime. The mill is equipped with quick change systems that allow for rapid roll changes, reducing the downtime required for maintenance and improving overall mill efficiency. The mill is also equipped with advanced safety systems that ensure the safety of the mill operators and prevent damage to the mill in the event of a malfunction. This slitting line is a machine that cuts a large coil of steel into smaller coils of specific widths. It's capable of handling a steel coil with a thickness of 2.5 millimeters, a width of 1,550 millimeters, and a weight of 20 metric tons. The process starts by loading a large coil of material onto the uncoiler, which unwinds the coil and feeds it through the slitting line. The material then passes through a series of rollers that flatten and straighten it before it reaches the slitter head. The slitter head contains a series of circular blades, spaced at specific distances from each other. The blades are adjustable, allowing the operator to set them to the desired width of the finished coils. As the material passes through the slitter head, the blades rotate and cut the material into multiple smaller coils of the desired width. After the material is cut, it passes through a series of tension devices that keep the smaller coils tight and prevent them from unwinding. The smaller coils are then collected on the recoiler, which winds them into tight, neat coils. This pipe production line helps produces pipes from steel coils. The production process involves several stages, including coil preparation, forming, welding, sizing, and cutting. To begin the process, the steel coil is loaded onto an uncoiler, which gradually unrolls the coil and feeds it into the next stage. The steel is then passed through a leveler that removes any irregularities in the material. After the leveler, the steel is shaped into a pipe form through a series of forming rolls. These rolls gradually bend the steel into a circular shape. Once the steel has been formed into a pipe shape, it is then welded together using high-frequency welding or submerged arc welding. This process fuses the edges of the steel together, creating a seamless pipe. Next, the welded pipe is passed through a series of sizing rolls, which shape the pipe to the correct dimensions. The sizing rolls also ensure that the pipe is perfectly round and has a consistent wall thickness. Finally, the pipe is cut to the desired length and undergoes any necessary finishing processes, such as surface treatment or coating, before being packaged for shipment. The CNC Pipe Bender by Eyebolt is a sophisticated machine designed to bend pipes with a high degree of accuracy and precision. The machine is equipped with a powerful hydraulic system that applies force to the pipe, which is then bent around a fixed bend die. The bend angle and radius are controlled by a CNC system that moves the pipe around the bend die with a series of programmed movements. The pipe bender can handle pipes with a diameter of up to 120 millimeters and a wall thickness of up to 8 millimeters. It has a maximum bend angle of 190 degrees and can achieve a high degree of repeatability and accuracy thanks to the CNC control system. To operate the machine, the operator first inputs the required bend angle, radius, and position of the pipe into the CNC control system. The pipe is then inserted into the machine, and the hydraulic system applies force to the pipe to bend it around the bend die. The CNC system controls the movement of the pipe to ensure that it follows the programmed path, resulting in a precise bend. The pipe bender is a versatile machine that can be used for a wide range of applications, including automotive, aerospace, and construction industries. It offers a high level of accuracy and repeatability, which makes it an ideal choice for manufacturing complex components with precise specifications. We are at the Zvezdochka Shipyard, located in Severodvinsk, Russia. The shipbuilding process begins with meticulous planning and design work. Over the course of many months, hundreds of engineers and design bureaus collaborate to create design documentation covering hundreds of square kilometers. These drawings and documents serve as blueprints for the ship's construction. In the hull shop, shipbuilders use templates and frame patterns to transform simple sheets of metal into the complex shape of a ship's hull. They carefully cut, bend, and manipulate the metal, working with hundreds, if not thousands, of individual blocks, parts, and elements. The goal is to give each piece its intended form, which contributes to the ship's overall nautical performance. The assembly and welding of sections is a labor-intensive stage in the shipbuilding process. Skilled welders, often working in teams, meticulously weld kilometers of seams using automatic and semi-automatic welding machines. These highly skilled workers, often part of a welding league of around 34 individuals, ensure the structural strength of the ship's hull by creating clean, durable welds. Shielding gases such as argon, carbon dioxide, or a mixture thereof are employed to protect the welding zone from the presence of oxygen in the air. Once the sections are assembled and welded, they are transported to the slipway for further construction. This involves using cranes to load the sections onto railway platforms. The impressive crane park of the workshop, consisting of 14 bridges and one gantry crane, operated by a team of 35 people, ensures precise movement and placement of the ship's components. At the slipway, the ship's hull begins to take shape. Workers with expertise in handling various materials, including special alloys like titanium and aluminum, meticulously construct sections of different shapes and sizes. These complex sections, including large deck sections and bottom parts, require powerful cranes and strengthened railway tracks to maneuver them into position with millimeter precision. The shipbuilding process also relies on advanced technological equipment. The hull shop has undergone significant modernization, with new equipment being put into operation. This investment in modern technology from leading European companies ensures efficiency and precision throughout the shipbuilding process. The The significance of the hull shop cannot be overstated. It has played a crucial role in ship construction and repair for over 55 years. The workshop has contributed to the development of various vessels, including nuclear submarines, fishing ships, and icebreakers such as the Lenin. The skilled workforce, comprised of both experienced workers and young professionals, ensures the workshop's continued success. MSC Meraviglia is a remarkable feat of engineering and construction, showcasing the intricate work and meticulous planning involved in building a state-of-the-art cruise ship. The construction process of this magnificent vessel involved an astounding 35,000 tons of steel, which was carefully crafted and assembled to create its massive hull. To meet the demanding construction schedule, a staggering 14,000 meters of steel was cut each week, highlighting the incredible productivity and efficiency of the shipyard. This relentless pace of steel cutting continued for over 12 months until the hull was fully formed. A remarkable 1.5 million hours of work were dedicated to this project, underscoring the dedication and expertise of the skilled workers involved. The construction process was divided into 50 mega blocks, which were assembled and joined together to create the final structure of MSC Meraviglia. To handle these colossal blocks, the shipyard employed the largest crane in Europe, a testament to the scale and complexity of the project. A notable feature of MSC Meraviglia's construction is the bulb design implemented in its hull. The bulb modifies the flow of water around the ship, reducing resistance and increasing its speed. This innovative design ensures optimal performance and fuel efficiency, allowing the ship to navigate through the water with enhanced speed and stability. In terms of propulsion, MSC Meraviglia features Azipod installation. These AZ-iPods are advanced propulsion systems that provide the ship with improved maneuverability and efficiency compared to traditional propulsion systems. This technological advancement allows the ship to move seamlessly through the water, providing a smooth and comfortable experience for its passengers. Once the construction of the hull and essential systems was complete, the ship underwent an elaborate painting process. A staggering 300,000 liters of paint were used to coat the vessel, ensuring its protection from the elements and giving it an attractive and polished appearance. With great anticipation and excitement, MSC Meraviglia finally touches the sea for the very first time, marking a significant milestone in its construction journey. The construction of the interiors on MSC Meraviglia showcases an impressive blend of efficiency, luxury, and entertainment, ensuring a captivating experience for passengers on board. The process begins with the installation of cabins, where a remarkable 2 cabins are built every hour to accommodate the ship's guests. To expedite this process, 2,244 pre-built cabins are brought in by truck and seamlessly inserted into the ship, ensuring a seamless and timely completion. Moving beyond the cabins, the construction efforts extend to various areas of the ship. The Galleria Meraviglia stands as a central hub, boasting a vibrant atmosphere and a wide range of amenities. Here, passengers can explore a 2-story infinity atrium, a visual marvel that exudes elegance and grandeur. Surrounding this breathtaking space, passengers will find 4 elegant pools, offering opportunities for relaxation and recreation. As passengers work up an appetite, the construction efforts focus on creating 12 dining areas, providing an extensive selection of culinary delights to suit every palate. The entertainment options on board MSC Meraviglia are nothing short of extraordinary. The construction process includes the creation of a magnificent 985-seat Broadway theater, designed to captivate audiences with exceptional performances. One of the ship's standout features is the 80-meter LED sky screen, the longest of its kind at sea. This massive LED screen serves as a mesmerizing backdrop for captivating visual displays and immersive experiences, enhancing the ambiance and entertainment on board. The construction efforts also extend to the Carousel Lounge, an exclusive venue dedicated to hosting Cirque du Soleil at sea shows. This collaboration between MSC Cruises and Cirque du Soleil brings world-class acrobatic performances and awe-inspiring spectacles directly to passengers, ensuring a truly unforgettable and unique entertainment experience. The production process of diesel engines at Navantia Diesel Engines Production Unit in Cartagena, Spain, follows a series of steps to ensure quality and reliability. The company specializes in manufacturing high and medium-speed diesel engines for naval and land-based facilities. Let's explore the production process in detail. Casting. The engine production starts with casting. Navantia has a foundry covering an area of 7,000 square meters. It has the capability to cast up to 60 tons of modular gray cast iron and up to 20 tons of alloy casting. Machining. After casting, the engine components undergo machining. Navantia employs flexible systems for machining, allowing them to manufacture castings with high added value. These systems use machine tools and devices with constant innovation and built-in quality monitoring. Inspection points and control programs ensure precision during the machining process. Assembly. The assembly lines cover an area of 5,000 square meters. Navantia's manufacturing system emphasizes modularity, quality, delivery time, and final cost. Skilled technicians assemble engines, generators, and engines for repair or overhaul, ensuring adherence to strict quality standards. Test beds and quality control. Navantia has test beds capable of handling a wide range of power and speed requirements. There are dedicated test beds for propulsion engines and generators. This allows thorough testing and verification of engine performance before they are delivered to customers. The quality department plays a crucial role in maintaining precision and reliability throughout the production process. They implement a system of quality control, continuous improvement, and calibration of control equipment. Material testing and measurements are performed in the laboratory. Cogsdill ZX tooling system is a cutting-edge solution that combines the precision and flexibility of Cogsdill tooling with the capabilities of Doosan DBC 130 horizontal boring machines. This partnership enables efficient and accurate machining of large parts that require multiple operations. The system comprises ZX facing heads, modular boring tools (MBT), and splining milling heads, seamlessly integrated with the Doosan DBC 130. The ZX range includes contouring and boring tools, capable of transforming simple two-axis CNC programs into a diverse range of machining operations. This flexibility allows for rapid adaptation to part changes through program modifications. Previously manual operations are transformed into CNC-controlled processes, boosting productivity, part-to-part repeatability, accuracy, and surface finish quality. The system handles tasks like boring, facing, contouring, threading, taper boring, grooving, profiling, and more. The ZX system requires a horizontal boring mill equipped with a programmable inner spindle that synchronizes with the outer spindle or milling sleeve. The axial movement of the inner spindle translates into radial cutting strokes for diameter control, while parallel table or column movement controls the cutting edge's axial position. This combination of movements corresponds to W and Z axes in most horizontal boring mills. The ZX system's controlled inner spindle movement facilitates radial cutter movement, while independently controlled column or table movement manages the axial position. Key advantages of the ZX tooling system include enhanced accuracy, improved part quality, surface finish, and rigidity for both roughing and finishing. The system's backlash-free actuation mechanism, modular design, and compatibility with various applications further contribute to its superiority. The manufacturing process of Andritz begins with rigorous design and engineering, where the pump's specifications are meticulously determined to meet the diverse requirements of different industries. Following this, the raw materials are cast using advanced techniques to create the intricate components that constitute the pump. Heat treatment is a critical step, enhancing the material's mechanical properties, ensuring durability and optimal performance under demanding conditions. Once treated, the components undergo precision machining through CNC-controlled milling processes, guaranteeing impeccable dimensions and tolerances. Andritz specializes in manufacturing multi-stage submersible pumps with exceptional wear resistance and operational reliability. This is achieved by incorporating advanced wear-resistant materials and meticulous engineering techniques, ensuring longevity even in challenging conditions. A distinguishing feature of Andritz centrifugal pumps is their submersible motors. These motors, either rewindable or with power capacities of up to 5,000 kilowatts, exemplify cutting-edge engineering. The integration of these motors into the pumps involves a seamless fusion of hydraulic and electrical engineering, enabling the pumps to operate effectively in submerged environments. The manufacturing process of turbines for hydropower plants is a fascinating blend of engineering, technology, and nature's energy. These turbines play a pivotal role in harnessing the immense power locked within flowing water and transforming it into valuable electrical energy. Among the leading players in this field, Andritz Hydro stands out with a legacy of more than 180 years and a remarkable track record of over 31,900 turbines installed worldwide, collectively producing a staggering 471,000 megawatts of power. The heart of a hydropower plant lies in its turbines, which are meticulously designed and crafted to adapt to diverse conditions. Andritz Hydro offers a spectrum of turbine types to match the unique requirements of each hydropower facility. For locations with high head applications, the Pelton turbine comes into play. These turbines rely on the kinetic force of water as it's directed through nozzles, striking the bucketed runner with precision. The result is a mechanical energy conversion process with minimal susceptibility to cavitation, achieving remarkable efficiency levels of over 92%. As the terrain transitions to lower heads, the Kaplan turbines fill the niche, designed for heads of up to 90 meters. These turbines, characterized by adjustable blades and horizontal shaft positioning, boast efficiency levels surpassing 95%. Their propeller-type design allows for outward reaction, altering water pressure as energy is extracted from the water's movement. The runner's stainless steel components, coupled with advanced design considerations, contribute to their high efficiency. In places where heads are exceptionally low, Andritz Hydro's bulb turbines come into their own. These turbines are recognized for their innovative horizontal shaft orientation, which reduces their size compared to traditional vertical arrangements. The adaptability of these turbines to varying conditions, along with their cost-effectiveness, has made them a cornerstone of hydropower solutions in such scenarios. Stepping into medium head terrain, the Francis turbine takes the stage. Capable of handling heads of up to 700 meters, these turbines are a versatile workhorse, known for their longevity, reliability, and robustness. Extensive research and development efforts have gone into optimizing their efficiency and operational range. Their ability to adapt to extreme conditions, both in single and multiple unit configurations, makes them a trustworthy choice for various energy applications. The Belo Monte hydropower plant, situated on the Xingu River in the Para-state of Brazil, marked a significant milestone with the inauguration of its 18th and final turbine. This mammoth project, developed by Norte Energia, involved the collaboration of Andritz Hydro. The plant boasts 18 vertical Francis units in the main powerhouse at Belo Monte and 6 bulb units at the complementary powerhouse in Pimentel. For the Pimentel site, Andritz Hydro provided 6 38.8 megawatts bulb turbine units, generator units, control systems, auxiliary equipment, and a complete 230 kilovolts, 69 kilovolts substation. Transporting the massive turbine components was a complex logistical feat. The journey from São Paulo state to Belo Monte encompassed road, sea, and river transportation. A specialized 100-meter-long and nearly 9-meter-wide truck was employed for the overland segment. The challenge also extended to navigating through 600 kilometers of the Amazonas and Xingu rivers. With a total capacity of 11,233 megawatts, Belo Monte provides clean and renewable energy to approximately 60 million people, contributing to Brazil's sustainable energy landscape. We're at the Belfort factory, the birthplace of the remarkable Arabelle steam turbine. The Arabelle steam turbine is set to be the largest ever manufactured, capable of producing 1770 megawatts of CO2-free electricity. The Arabelle steam turbine is composed of 4 modules: high pressure, intermediate pressure, and 3 low pressure modules, each containing a rotor and casing. Notable features include the low pressure rotor, over 8 meters in diameter, and the longest stage blade ever made at 1.9 meters. Next, we explore the generator building, where the stators of Unit 1 and Unit 2 are being prepared for stacking. Inside the generator stator of Unit 1, the stacking of the magnetic core is a meticulous process involving 360,000 plates. The rotor, upon completion, will contain 370 copper bars forming the rotary winding. ready to be driven by the Arabelle steam turbine and generate electricity. Doosan's steam turbine manufacturing technology is underpinned by a modular design philosophy that seamlessly integrates proven operational elements, differentiated only by flow part dimensions, resulting in reliable and tailored solutions for customers. The company optimizes designs by blending standardized modular components with bespoke design elements to meet individual customer requirements. The foundation of Doosan's manufacturing excellence dates back to the development of their first steam turbine in 1904 by Škoda Works, now Doosan Škoda Power. Over the years, Doosan's commitment to innovation and customer satisfaction has led to the creation of advanced steam turbine technologies that deliver high efficiency and exceptional performance. Doosan's expertise in steam turbine technology is evident in their advanced aeroblade design. With over a century of experience in both impulse and reaction technology, the company's proficiency shines through in their ability to create advanced blades with three-dimensional designs. This approach ensures that their turbines achieve the highest levels of efficiency while maintaining quality performance over time. To achieve optimized performance, Doosan employs advanced sealing technology. Recognizing the significance of sealing for modern steam turbines, the company has developed advanced sealing solutions that minimize operational clearances and reduce leakage losses. Their portfolio includes a range of sealing technologies, including brush seals, abradable coatings, retractable seals, and honeycomb seals, all contributing to remarkable efficiency improvements. Incorporating innovative manufacturing techniques, Doosan employs welded rotors that facilitate the creation of large, low-pressure turbine rotors with improved dynamic behavior during operation. These welded rotors enable faster startup and loading by reducing stress levels compared to traditional monoblock rotors. Doosan's special technology for heterogeneous rotor welding allows for the combination of materials with optimal properties in different sections of the rotor flow path. This innovation leads to the production of creep-resistant materials in the high-temperature sections and ductile high-strength materials in colder areas, ultimately enabling the design of high-power output turbines in a single casing compact arrangement. Furthermore, the assembled diaphragm design demonstrates Doosan's commitment to precision and efficiency. By securing inserted nozzle blades into outer and inner rings with mechanical pins, deformation is minimized, resulting in improved manufacturing accuracy and a highly efficient flow path. In the picturesque ancient city of Verona, located in northern Italy, the fusion of history and innovation becomes evident through the fabrication of a cutting-edge turbine generator unit at the Chievo Dam Hydropower plant. This historical city, renowned for its medieval center and hosting the Verona Opera Festival each summer, welcomed a remarkable technological advancement that seamlessly blends with its surroundings. The Chievo Dam Hydropower plant project began with a vision to harness the untapped hydraulic power of an abandoned ship lock while preserving its flood discharge capabilities. This ambitious endeavor required creative engineering solutions, and the hydromatrix concept from Andritz Hydro proved to be the linchpin in turning this vision into reality. At the heart of the Chievo Dam hydropower plant is a meticulously fabricated steel module situated at the downstream end of the lock. This module houses the intake trash rack and 5 Straflow matrix turbine generator units, each with individual draft tube gates that allow for independent operation. The compact size of the Straflow matrix turbines was crucial in this space-constrained location, providing an advantage for projects where limited space is available. The turbine runner blades, integral to the Straflow matrix turbines, were crafted with precision from corrosion-resistant steel. These blades were seamlessly attached to the runner hub, forming an essential part of the turbine's operation. A meticulous welding process ensured the integrity of the turbine runner, while advanced permanent magnet technology facilitated synchronous generator operation, seamlessly connecting the plant to the local grid. The final assembly of these intricate components took place at Andritz Hydro's own generator workshop in Austria. The generator rotor, stator, distributor cone, and intermediate flange came together to create a functional and efficient turbine generator unit. The assembly process was streamlined due to the high level of prefabrication, allowing for short assembly times. The Fermat WFT13 CNC is a top-of-the-line rotary table CNC horizontal boring machine that offers exceptional precision and power for various machining applications, with a particular emphasis on helical interpolation. Equipped with an automatic tool changer and a micro-indexing head, this bed milling machine stands out as a versatile and efficient solution. The key component that enhances the machine's capabilities is Fermat's automatic micro-indexing milling head, the UHA MI30. With an impressive power output of 30 kilowatts and a torque of 1,600 Newton-meters, this milling head can handle demanding machining tasks with ease. Moreover, its micro-indexing capabilities of 0.001 degrees 0.001 degrees enable precise and intricate machining operations, making it perfect for helical interpolation tasks. One of the standout features of the WFT13 CNC is its robotic tool changer. The 6-axis high-tech robots deliver swift and efficient tool changes, ensuring minimal downtime during machining operations. This automated tool changer can seamlessly switch between multiple positions, accommodating even heavy tools weighing up to 75 kilograms. As a result, the machine can maintain a continuous workflow without the need to pause for manual tool changes, which significantly boosts productivity and saves valuable machining time. Helical interpolation is a crucial operation in various industries, such as aerospace, automotive, and manufacturing, where the creation of complex, precise, and smooth curves is essential. The WFT13 CNC's capabilities, combined with the automatic micro-indexing head and robotic tool changer, make it an ideal choice for tasks involving helical interpolation. The machine can execute intricate cutting paths with utmost accuracy and efficiency, meeting the high-quality standards demanded by The 5-axis milling turning center CP6000 by Heller is a powerful machining solution designed for combined milling and turning operations on a single machine, known as combined processing. Key features of the CP6000 5-axis milling turning center include a universal 5-axis setup with the 5th axis in the tool and a DDT direct drive turning rotary table. This setup enables simultaneous 5-axis machining and 5-sided machining, as well as turning with positioned rotary axes. The machine can utilize spindle units with swivel head or tilting head kinematics, providing additional versatility for various machining tasks. The CP6000's robust machine design, coupled with high-torque spindle technology, ensures stable and efficient performance during the machining process. By reducing the number of clamping positions and enabling complete machining in one setup, the CP6000 optimizes part costs, saving time and resources. The machine is suitable for a wide range of parts and materials, making it highly adaptable to diverse manufacturing requirements. For series production, machines equipped with a pallet changer, CP, are optimal, while those with table loading, CORT, are well suited for workshop-based production and small batch sizes. Moreover, the CP6000 is easily automatable with workpiece or pallet automation systems, further enhancing productivity. The machine concept of the CP6000 is the result of comprehensive simulations and structural dynamic examinations during the development phase. Its crossbed and traveling column design, constructed with topology-optimized structural components from cast iron, ensures high stability and effective damping of forces. The thermo-symmetrical design and optimized flow of forces contribute to the machine's precision and productivity in both milling and turning operations. The 5-axis machining centers HF series by Heller are cutting-edge machines designed to deliver superior productivity and precision, making them ideal for modern production processes. These machining centers allow for 5-sided and simultaneous 5-axis machining, enabling a wide range of tasks to be performed on a single machine. They are known for their high productivity, flexibility, ease of operation, and low maintenance requirements. Available with either a pallet changer or table loading, these machines offer versatility to cater to various production needs. The second generation of the HF series represents an evolution in terms of performance and precision. It introduces new spindle units with enhanced capabilities and incorporates the Heller Zero spindle system, which contributes to reduced life cycle costs. The addition of a second drive in the Z-axis enhances the machine's versatility, making them suitable for single-part production as well. With the renowned Heller DNA of productivity, precision, and reliability, these 5-axis machining centers promise improved performance, accuracy, and flexibility in producing high-quality workpieces. Key features of the 5-axis machining centers HF, horizontal 5-axis machining. The HF series employs a horizontal spindle for optimal chip evacuation, leading to improved machining efficiency. Universal machining. These machining centers feature a 5th axis integrated into the workpiece, allowing for highly dynamic and productive machining. Swiveling NC rotary table. Standard on these machines is a swiveling NC rotary table with counterbearing and AB kinematics. This ensures smooth and precise movement during machining processes. Mill turn option. The HF 5500 model offers a unique combination of milling and turning capabilities, providing greater flexibility in manufacturing complex parts. Equipment packages. The HF series offers 3 equipment packages: Power, Speed, and Pro, catering to different production requirements. The Speed and Pro options are particularly notable for their short chip-to-chip times and high axis speed. Optimized 5-axis machining. The machines support both simultaneous and position 5-axis machining, allowing for greater efficiency and accuracy in various tasks. Spindle units. The HF machining centers are equipped with HSKA 63 or HSKA 100 spindle units, ensuring excellent cutting performance and precision. Gantry drive optional. For enhanced application versatility, the HF series offers an optional gantry drive in the Z-axis, further expanding the scope of operations. Optimum accessibility. The design of the machining centers ensures easy access for operators, simplifying both operation and maintenance tasks. Advanced control technology. The machines are equipped with a main operating unit featuring a 24 inches multi-touch screen and Heller operation interface, providing an intuitive and user-friendly experience. Automation ready. These machining centers are easily automatable, allowing for seamless integration with workpiece or pallet automation systems. Pallet changer or table loading. The option of choosing between a pallet changer or table loading makes them suitable for both series production and workshop-based manufacturing. When machining a mold component made of steel on the 5-axis machining center HF3500, Heller collaborates closely with their trusted technology partner, Monopile, to ensure the highest level of precision and surface quality for the workpieces. The steel workpiece is securely clamped onto the machining center's swiveling NC rotary table, which enables access to multiple sides of the component without the need for repositioning. This 5-axis capability allows for the implementation of complex machining operations in a single setup, reducing production time and minimizing errors. As the machining process commences, the HF3500's horizontal spindle, equipped with a high-performance cutting tool from Monopile, starts removing material from the steel workpiece with exceptional accuracy. The spindle's precise rotational control combined with the multi-axis movement of the machine ensures that even intricate features and fine details are machined to exact specifications. Throughout the process, the HF3500 maintains a stable and rigid machine structure, preventing any vibrations that could affect the surface quality and dimensional accuracy of the mold component. The machining center's advanced gantry drive in the Z-axis further enhances stability during heavy cutting, ensuring optimal cutting conditions. Thanks to the optimized interaction between the machine, tool, and cam strategy, the HF3500 achieves outstanding surface quality, leaving the mold component with a smooth and flawless finish. The stringent quality control measures implemented by Heller guarantee that the final workpiece meets the most stringent industry standards. The Imugi Circ GF Indexable Thread Mill is a cutting-edge solution designed to deliver maximum confidence, depth, versatility, and cost-effectiveness in thread milling operations. It harnesses the advantages of thread milling technology, allowing users to produce threads with impeccable form, finish, and dimensional accuracy. Moreover, it simplifies the machining of challenging materials, mitigating the risks associated with tap breakage. This thread mill enables full bottom threading and precise control over thread depth, ensuring optimum positional accuracy. Its CNC offset feature empowers users to regulate the pitch diameter with ease. Additionally, it offers the convenience of a single tool for both right-hand and left-hand threads, as well as for both through and blind holes. This part shows CNC machining brass with some thread milling. Thread milling is a cutting-edge technology that offers numerous advantages in producing threads with exceptional precision and efficiency. It involves using a thread milling cutter to create threads in a workpiece, such as screws, bolts, and other threaded components. Here are some key advantages of thread milling technology: excellent form, finish, and dimensional accuracy. Thread milling produces threads with superior form and surface finish. The cutting process is more controlled compared to traditional methods like tapping, resulting in threads with precise dimensions and reduced tolerances. This high level of accuracy is crucial for applications where threads must fit perfectly and securely. Easy machining of difficult materials. Thread milling is particularly advantageous when working with difficult-to-machine materials like exotic alloys, stainless steel, hardened steel, and heat-resistant materials. These materials can pose challenges for traditional threading methods due to their hardness and toughness. Thread milling allows for smoother cutting and reduces the risk of tool wear and breakage. Elimination of tap breakage. One of the significant drawbacks of tapping is the risk of tap breakage, especially when tapping deep holes or working with tough materials. Thread milling eliminates this concern since it uses a single solid cutter instead of a fragile tap, leading to a more reliable and secure machining process. Full bottom threading and precise thread depth control. Thread milling allows for full bottom threading, meaning the thread can be extended all the way to the bottom of a blind hole. This ensures that the threaded part has maximum strength and engagement. Additionally, thread depth can be accurately controlled using CNC offset programming, providing consistent and precise results. Optimum positional accuracy. Thread milling is well suited for CNC machining, enabling high positional accuracy. This is especially beneficial when producing intricate parts with multiple threaded features that require precise alignment. One tool for right-hand and left-hand threads. Unlike tapping, where separate tools are required for right-hand and left-hand threads, thread milling cutters can produce both types of threads using the same tool. This simplifies the machining process and reduces tooling costs. Suitable for through or blind holes. Thread milling is versatile and can be used for both through holes and blind holes. It offers flexibility in creating threads in various types of workpieces and hole configurations. Small controllable chips. Thread milling generates small manageable chips, reducing the risk of chip entanglement or bird nesting. This helps maintain a clean and efficient machining process. Less cutting pressure for thin-walled parts. In comparison to tapping, thread milling exerts less cutting pressure, making it a better choice for machining thin-walled parts. The reduced force minimizes the risk of workpiece deformation or damage. Heller's production systems offer flexible and efficient solutions for the complete machining of crankshafts and camshafts. These systems can be utilized as standalone machines or integrated into interlinked production systems, providing comprehensive expertise across the entire process chain. The RFK system focuses on external and internal milling of crankshafts. External milling is a highly productive method, commonly used in mass production for small to medium-sized crankshafts. It involves machining concentric and eccentric bearing points, cheek faces, cheek outer diameters, and special contours. The process utilizes external cutters whose profiles are tailored to the specific profile to be milled. For machining crankpins, two interpolating NC axes are positioned eccentrically to the workpiece center and/or the concentric main bearings of the crankshafts. The workpiece generates the feed rate while the tool generates the cutting speed, making the process efficient and precise. The DRZ system is designed for turn chasing of crankshafts, providing another method of pre-machining. MCC-15, on the other hand, focuses on milling, drilling, and thread cutting of crankshafts, adding further versatility to the production process. The RFN system specializes in external milling of camshafts, rounding out the capabilities of Heller's production systems for both crankshafts and camshafts. The advantages of Heller's crankshaft production systems include customizability, allowing process engineering to be tailored to specific requirements, and high productivity due to the use of advanced machining technologies. With the option to use multiple machining units simultaneously, the systems can efficiently handle complex tasks such as simultaneous machining of main bearings and crankpin journal profiles in a single setup. Heller's expertise also allows them to implement other technologies and combinations, providing comprehensive solutions for their automotive industry clients. Additionally, the precision achieved during external milling eliminates the need for rough grinding, saving time and resources while maintaining the highest quality standards. The Haas Street 20Y Y-axis CNC turning center is a high-performance machine that offers exceptional value for workshops in the manufacturing industry. This model is part of the ST20 series, which comes with various improvements in performance and features, making it an attractive choice for those seeking reliable and efficient CNC turning solutions. One of the standout features of the Saint 20Y is its Y-axis capability, which provides 101 millimeters of travel, allowing for off-center milling, drilling, and tapping. This versatility enables the machine to perform multiple operations on one platform, reducing handling time, increasing throughput, and improving overall accuracy. With high-torque live tooling and a servo-driven C-axis as standard, the Saint 20Y offers 4-axis capability, further enhancing its machining capabilities. The machine's design includes more compact and rigid castings, leading to increased stability and cutting performance. Despite these enhancements, the Saint 20Y maintains a smaller footprint compared to its predecessor, ensuring efficient use of workshop space. Moreover, the Saint 20Y boasts a larger spindle bore of 2.5 inches, allowing for increased bar capacity and accommodating larger workpieces. The machine's Z-axis travel has also been improved, providing more flexibility in machining operations. In addition to its impressive technical specifications, the Saint 20Y comes with user-friendly features such as standard Wi-Fi and an optional auto door for added convenience. The machine is equipped with a 15-inch color LCD monitor, memory lock key switch, spindle orientation, USB port, and rigid tapping, further enhancing its ease of use and productivity. As with all Haas machines, the Saint 20Y Y-axis CNC turning center is manufactured in the USA, ensuring high-quality construction and adherence to stringent standards. The Haas Street 10Y is a compact yet powerful CNC lathe offered by Haas Automation, designed to deliver excellent performance while occupying minimal floor space. With its 305 mm turning diameter, 356 mm turning length, and 413 mm swing over the front apron, this machine provides a generous workspace for a variety of turning operations. It is a valuable addition to workshops seeking a second-op machine or those facing space constraints, making it an ideal choice for startup shops or as an entry into CNC turning. One of the standout features of the ST10Y is its Y-axis travel capability, providing 101 mm of movement, plus or minus 50.8 mm from the center line. This allows for off-center milling, drilling, and tapping, enhancing the machine's versatility and enabling complex machining operations in a single setup. Additionally, the Saint 10Y is equipped with high-torque live tooling and a servo-driven C-axis, offering 4-axis capability to further expand its machining capabilities. The machine comes standard with a 6-inch, 165mm hydraulic chuck and a 12-position bolt-on tool turret, providing ample tooling options for various jobs. Its 15 horsepower peak vector drive spindle can reach speeds up to 6,000 revolutions per minute, enabling high surface feed rates and efficient cutting. For enhanced productivity and convenience, the Saint 10Y offers various optional features, including a belt-type chip conveyor, hydraulic tailstock, automatic tool probe, live tooling with C-axis, automatic parts catcher, and high-pressure coolant systems, among others.
The closed die forging process for manufacturing an eyebolt involves several sequential steps. It begins with heating the billet, followed by placing it into a single-ended press to form a round block. The purpose of this step is to prepare the billet for further shaping. Once the billet is heated and placed in the press, the worker clamps the workpiece and inserts it into a hammer forging machine. In this machine, the round head of the eyebolt is flattened through the force of the hammer, imparting the desired shape to the component. After the initial shaping, the workpiece is transferred to a closed die forging machine. The worker and the machine collaborate to reverse the bolt billet repeatedly until a hole is formed in the middle. This process involves compressing and deforming the metal under high pressure, gradually transforming it into the desired eyebolt shape. Subsequently, the worker clamps the workpiece onto another press specifically designed for stamping out the excess material. This step eliminates any surplus metal, ensuring the eyebolt reaches its final dimensions and shape. To enhance the properties of the eyebolt, it undergoes a rapid dip in water, known as quenching. After quenching, the eyebolt is returned to the closed die forging machine for one final operation. Finally, the eyebolt undergoes a grinding process, where any remaining rough edges or imperfections are smoothed out. Grinding provides a refined surface finish and prepares the eyebolt for subsequent inspections and quality checks. The first step in manufacturing padlock is fabrication of the shackle, the U-shaped metal part of the padlock. The steel material is cutted into short pieces of the required length. These steel pieces serve as the foundation for creating the U-shaped shackle. The next step is lathing one end of the piece of steel. By lathing one end of the steel piece, the desired shape and design features of the shackle are achieved. After the lathing process, the steel piece is ready for bending. The steel piece is placed in a bending machine, where it is clamped and manipulated to achieve the desired curvature. Once the steel piece is bent into the U-shape, it undergoes heat treatment. Heat treatment is a controlled process that involves subjecting the metal to specific temperatures and cooling cycles. This treatment enhances the mechanical properties of the shackle, improving its strength, hardness, and durability. Heat treatment ensures that the shackle can withstand external forces and provides optimal security for locking low and medium responsibility premises. After the shackle is fabricated, the next step is manufacturing the lock body. The lock body provides the structure and housing for the internal components of the padlock. The process begins by stamping steel coils into uniform pieces that will form the body of the lock. These stamped pieces are then stacked together, aligning them properly. The stacked pieces are then dipped in molten aluminum, which coats and solidifies around the stack, forming the lock body. This aluminum coating adds an additional layer of protection and corrosion resistance to the padlock. The lock cylinder is made of copper, contains small holes. The lock cylinder plays a crucial role in the operation of the padlock as it houses the mechanism that interacts with the key to lock and unlock the shackle. In the assembly process, cylindrical pins are inserted into these holes. The pins are carefully sized and positioned to correspond with specific grooves on the key. When the key is inserted into the lock cylinder, the pins align with the grooves, allowing them to be raised to the correct height within the chambers. This alignment is crucial for the lock to operate smoothly. The use of copper for the lock cylinder ensures durability, while the precise positioning of the pins enables effective engagement with the key. During the assembly of the lock cylinder, the key is also fabricated. Finally, all the parts, including the shackle, lock body, and key, are assembled into the padlock. The shackle is connected to the lock body, allowing it to secure and release the lock. The key is inserted into the lock, engaging the cylinder disc mechanism to unlock or lock the shackle. To ensure the quality and functionality of the padlock, thorough testing is conducted. The completed padlocks undergo various tests, including durability, strength, and security tests. These tests simulate real-world usage conditions and verify that the padlock meets the required standards and specifications. Only the padlocks that pass the testing phase are deemed ready for distribution and sale. Pliers are a common tool used for gripping and manipulating objects. The manufacturing process of pliers involves several steps, starting with three main components: the handles, the pivot pin, and the jaws. The production begins with metal blanks, which are shaped by metalworkers. The blanks are initially heated in a powerful electric melting furnace. Within seconds, the steel becomes red hot. The workers then place the heated blanks onto a stamped mold. A massive press exerts several tons of force on the blanks, shaping them according to the mold. It takes up to 4 strikes on each blank to achieve the desired form. Once shaped, the blanks are placed on another press that removes excess metal, resulting in the production of a single pair of pliers. To create the gripping teeth on the jaws, the halves of the pliers are placed into a machine. Tiny sheets of steel, dozens in number, are cut by a stream of coolant and cooling mist. As the halves are removed from the machine, they already have a series of excellent teeth. The steel of the pliers needs to undergo a process called hardening to make it strong. The halves are subjected to a 2-hour process in a gas furnace at a temperature exceeding 800 degrees Celsius. Subsequently, the steel is immersed in salt water for rapid and uniform cooling. Laser treatment is then applied to the teeth of the pliers to make them even harder and more durable. At this stage, the pliers are ready for assembly. A worker inserts the pivot pin and joins the two halves together. The pin is securely fastened by a high-speed rotating machine that applies significant force and friction. The combination is firmly fixed. Flat nose pliers, on the other hand, are assembled differently. The tool is placed under a press that uses heat and high pressure to firmly secure the pivot pin. The worker then places the pliers between two grinding wheels, which are used to smooth the surface and align the pin with the flat nose surface. Emulsion is used to prevent overheating of the steel as the wheels wear down the pin until it is level with the surface of the flat nose pliers. The flat nose pliers are subsequently sent to a gas furnace for an additional 2 hours of heat treatment, which is also a hardening process. After removal from the furnace, they are immersed in an oil solution. Unlike the pliers, which were rapidly cooled in a salt solution, this process allows the protective coating to adhere to the steel gradually. Steel is a refined material, so it is crucial to carry out the heat treatment process meticulously. Otherwise, the metal's quality will be compromised. After the heat treatment, the pliers are dipped in a bath containing an anti-corrosion solution. This helps protect the steel from rust and lubricates the pivot joint. A robotic arm presents the pliers to a grinding belt, which polishes all surfaces except for the handles, leaving them smooth. The company's logo and product number are then engraved on the pliers using a laser. The handles of hundreds of pliers are immersed in a liquid vinyl bath, ensuring a seamless and comfortable grip. The pliers are heated before immersion, allowing the coating to adhere to the steel. Finally, the pliers are sent into an oven where the protective coating hardens, providing a cushion-like grip and making them easier to hold in the hand.
The expanded metal machine APV125M4 is used for manufacturing expanded metal sheets with different thicknesses and stiffness. The machine is equipped with a set of knives and a razor mesh, and it can produce up to 760 meters per square of grid shift. The machine's dimensions are 3,400 by 3,100 by 1,600 millimeters, and it weighs 2,300 kilogram. The machine works by feeding a metal sheet into it, which is then cut and stretched by the set of knives and razor mesh. The mesh footage counter keeps track of the amount of mesh produced, and the net roll winder collects the finished mesh. The machine can manufacture both plaster and protective grids by adjusting the thickness of the jumpers from 1.0 millimeters to 4 millimeters. The machine components are made with a 5-time power reserve, which ensures that the machine can withstand heavy workloads. The machine uses tapered bearings that can pull the backlash, which is important in expanded exhaust machines. The bearings and belts used in the machine are standard and can be found in any store. The machine's motor power is 5.5 kilowatts and the voltage is 380 volts. The machine is also equipped with an addle table to support the iron sheet and a side table to support the grid sheet. The production of rolling lines is a crucial process for meeting the high demand for metal profile products, such as corrugated board and metal tiles. The Lipetzik roll forming plant has been developing and manufacturing rolling mills for work with smooth sheet metal. The principle of forming a profiled sheet involves passing a smooth sheet of metal sequentially through the stands of a rolling mill, each of which changes its forms more and more until the desired profile is achieved. The finished products are then cut into the required length. The manufacturing of rolling line equipment begins with cutting high-quality rolled metal into blanks for future rolling parts. The profiling rollers are machined on high-precision machining centers, and the frames of future workpiece mills are assembled and welded. The shafts are assembled sequentially in strict accordance with design documentation, with each video clip connected to the shaft through a key. The assembled shaft is fixed on both sides with nuts and is then ready for painting. Gears are also being manufactured at the same time in another workshop area. The equipment system includes a variety of modern CNC machines to help the parts to be manufactured with the best quality and minimal tolerances. The frame part is welded and painted. Painting. After the profiling rollers are assembled, they are painted. The frames of the workpiece mills are also painted after they are welded. The unwinder roll spacer's primary function is to securely fix the roll of metal on the drum unwind and control the speed of the roll unwinding. During the assembly process of a rolling line, the unwinder roll spacer is installed between the unwinder and the rolling mills. This allows for the parallel unwinding of the metal roll while the metal sheet is being fed into the rolling mills. The unwinder roll spacer is designed to automatically control the unwinding speed of the metal roll, which is dependent on the speed of the sheet feed. The assembly of the rolling camp involves installing special frame hole Clyde mounting racks between the racks and installing lower and upper shafts. The racks are connected by a jumper oval and temporarily fixed in the up position. The clearance between the shafts is adjusted later. The guillotine scissors are used to cut the finished profile into sheets, which are then sold to customers for their needs. The guillotine knives are made in high-precision machining centers, and if the shape of the knife is different from the geometry of the finished profile for at least a few hundredths of a millimeter, the funds will be unevenly sheared off in the sheet, leaving burrs. To ensure that the knives serve for a long time, they are first heated to high oven temperature and then cooled in water or oil. The finished knives are bolted and fixed on the frame and painted after the assembly of the rolling camp. Vertical racks and adjusting screws. Once all the parts are ready, the vertical racks are installed and the adjusting screws are fixed between them. Horizontal connections are installed between the racks, and the nuts on the racks are tightened by the master. Another master pulls the chain and connects their castle, and then all the shafts will rotate synchronously. Electrical wiring. The electrical wiring is then installed, and the terminal actuators are connected to the remote control. Machine setup. Finally, the machine is set up, and the alignment of all stands is established. The required gap between the upper and lower rollers is set, and the metal roll unwinder and rolling mill shear guillotine system are set up for automatic control. The entire rolling line machine then operates as a single unit, ready to be shipped to the customer. Unwinding. The sheet are fed into the rolling line, and the unwinder roll spacer securely fixes the roll of metal on a drum. The roll unwinding speed is controlled automatically depending on the speed of the sheet feed. Forming. As the metal sheet is fed through the rolling line, it is sequentially passed through the stands of the rolling mill, each of which changes its form. The profiling rollers change the shape of the metal sheet until it takes on the desired profile, in this case, a corrugated board. This process involves the use of a guillotine scissors, which cut the finished profile into sheets of the required length. Cutting. Once the corrugated board has been formed, it is cut to the required length using the guillotine scissors. Roll forming is a metal manufacturing process that involves the continuous bending of a long strip of metal through a series of rolls until it achieves the desired shape. Steel Forming Systems is a company that specializes in roll forming and offers a range of services to help customers meet their metal component manufacturing needs. The process of roll forming at Steel Forming Systems starts with the engineering and development of tooling. Once the company has consulted with the customer and gained a full understanding of their product and needs, a distinct program is developed to manufacture the most precise part at the highest rate of production. The expert technicians take this information and program the equipment to exact specifications in order to achieve the highest quality and product. One example of roll forming is the production of a shelf, which starts with a coil of rolled stock. The material is uncoiled by the mill and passes through a series of pre-pierced dies where notches, slots, and holes are added to the part before it proceeds to undergo roll forming. The material passes through a series of roller dies, with each pass carefully making small changes to the shape of the steel until the desired profile is achieved with a minimum of stress to the stock. Finally, the part passes through a cut-off die where it is cut to the desired length, and a technician inspects the part to ensure it meets all of the customer's specifications and quality requirements. Another example of roll forming is the production of a wall stud, which requires galvanized steel due to the nature of the product. This mill forms a more complex profile requiring more passes, with post-pierced elements added before or after the part is roll formed depending on what makes for a more efficient operation. Another example of roll forming is the production of a wall stud, which requires galvanized steel due to the nature of the product. This mill forms a more complex profile requiring more passes, with post-pierced elements added before or after the part is roll formed depending on what makes for a more efficient operation. When welding is required, Steel Forming Systems offers robotic welding, which creates cost savings through a reduction in labor costs and an increase in the number of parts produced per hour. Robotic welding also increases the quality of the parts produced as the machine creates quality welds every time. Additionally, resistance welding is available as a solution, which allows electricity to pass from the electrode and through the part to create heat and allow the two parts to permanently join. Finally, automated assembly is offered as a complement to roll forming. Steel Forming Systems provides solutions that may help complete the component or assembly after it has passed through the roll forming process. For example, an automated screw machine is used to apply screws to parts with a specific torque level to ensure the proper quality of each part. The production line focus on automated assembly reduces production times and increases the customer's profit margin. The manufacturing process of hot forging products in the Isaac factory is a multi-step process. The process begins with the raw materials, which are steel bars of various qualities and sizes. Once the steel bars have been selected and moved to the hot forging section, they are loaded onto a bench and welded together to create longer lengths that can be fed into the furnace for heating. A computer system tracks the movement of the steel bars from the raw materials section through the heating process and into the forging machines, ensuring that each bar is accurately monitored and accounted for throughout the production process. The furnace heats the steel bars to a specific temperature, which varies depending on the type of steel being used and the desired properties of the final product. Once the bars have reached the desired temperature, they are fed into a press machine that shapes the steel into the desired form. The press machine used in the hot forging process at this factory is a powerful piece of equipment capable of exerting immense pressure on the steel bars. This pressure is used to shape the steel into the desired form using specialized dies and other tools that are carefully chosen for each specific product. The hot bars are fed into the press machine, where they are positioned between the dies. The dies are designed to match the shape of the finished product, so the steel is shaped as it is squeezed between them. The press machine applies pressure to the dies, forcing the steel to flow into the desired shape and fill every corner and cavity of the die. In addition to the press machine, other tools and equipment are used to help shape the steel. For example, some products may require the use of hammers or other tools to create specific details or shapes. After the initial forging process, the products are trimmed and shaped using specialized tools to remove any excess material or burrs. They are then transferred to a finishing station where they are inspected for quality and any final adjustments are made. Mastercam is a leading software application for computer-aided manufacturing, CAM, offering a range of powerful tools and features to facilitate the production of complex parts with high precision and speed. One of the most impressive capabilities of Mastercam is its dynamic motion technology, which allows for optimized machining processes that reduce cycle times, extend tool life, and enhance surface finish. The Cypher & Steiner Precision Parts Company is a perfect example of how Mastercam dynamic motion technology can be used to produce extraordinary parts. The company used Mastercam to design and manufacture a high-performance wheel rim with complex geometry and tight tolerances. Using Mastercam's advanced toolpath algorithms and dynamic motion technology, Cypher & Steiner was able to achieve significant improvements in their machining operations. The toolpaths were optimized to minimize tool engagement and reduce cutting forces, resulting in a smoother and more efficient machining process. The dynamic motion technology allowed the tool to maintain a constant chip load, even when machining complex contours, preventing excessive wear on the tool and extending its lifespan. Furthermore, Mastercam's simulation capabilities enabled Cypher & Steiner to verify the machining process and detect potential errors before they occurred. This feature ensured that the machining process was optimized for the highest level of precision, reducing the risk of material waste and rework. The DMG Mori NLX2500SY is a highly advanced CNC machine used for precise machining operations in various industries, including the hydraulic cylinder component division. This machine is equipped with state-of-the-art technology that allows for the creation of highly complex and accurate parts. In this video, we will explore the process of machining a component on the DMG Mori NLX2500SY in the hydraulic cylinder component division. The hydraulic cylinder component division is responsible for the production of hydraulic cylinders, which are an essential component of various hydraulic systems. These cylinders are used in a wide range of applications, including construction equipment, agricultural machinery, and industrial machinery. In order to produce high-quality hydraulic cylinders, precise machining is required. This is where the DMG Mori NLX2500SY comes into play. The first step in machining a component on the DMG Mori NLX 2500SY is to create a CAD, computer-aided design, model of the component. This model is then used to program the machine's CNC, Computer Numerical Control System. The CNC system controls the machine's cutting tools and movements, allowing for precise machining operations. Once the CNC program is created, the component is loaded onto the machine's workpiece holder. The NLX 2500SY is equipped with a twin spindle and twin turret system, allowing for simultaneous machining operations on both ends of the component. This significantly reduces machining time and improves efficiency. The first machining operation is typically roughing, where excess material is removed from the component. The NLX 2500SY is equipped with high-speed cutting tools and a powerful spindle motor, allowing for fast and efficient material removal. The machine's cutting tools are also equipped with coolant, which helps to reduce heat and prevent tool wear. After roughing, the component is ready for finishing. This is where the NLX 2500 size precision comes into play. The machine is capable of making extremely accurate cuts, ensuring that the finished component meets the required specifications. The machine's twin spindle and twin turret system also allow for complex machining operations, such as milling, drilling, and tapping. Once the machining operations are complete, the finished component is removed from the machine and inspected for quality. The NLX 2500 size precision and accuracy ensure that the component meets the required specifications, and any defects or errors can be quickly identified and corrected. The S-81 Isaac Perel is a groundbreaking submarine that is set to launch a new era for the Spanish Navy. This impressive vessel, christened in Cartagena, Spain, is one of the largest non-nuclear submarines in the world, weighing in at 2,965 tons. The S-81 Isaac Perel boasts the S-80 Plus design, which incorporates a bioethanol fuel cell AIP, air-independent power system, known as BEST, bioethanol stealth technology. This system offers several advantages over other AIP systems. It utilizes bioethanol as fuel, which can be easily sourced and reformed after use, eliminating the need for separate hydrogen storage tanks required by other AIP submarines. Equipped with a formidable arsenal, the S-81 Isaac Perel carries three primary weapons: the DM-2A4 heavyweight torpedo, UGM-84 sub-harpoon anti-ship missile, and SAES seabed mines. Additionally, although the order for UGM-109 Tomahawk land attack cruise missiles has passed into history, the submarine retains the capability to carry them if acquired in the future. This unique feature places the Spanish Navy in an elite group of submarine operators with a potential first-night strategic strike capability among non-nuclear NATO submarines. The submarine is named after Isaac Perel, a Spanish naval officer and engineer who designed the world's first all-electric submarine. Commissioned into the Spanish Navy in 1889, Perel's pioneering work predates the first submarines of the U.S. Navy and Royal Navy by more than 10 years. In recognition of his contributions, the Spanish Navy has previously named 3 submarines. Compared to the Scorpene class, the S-80 Isaac Perel features a wider hull and a greater length, allowing for an extra deck level and enhanced storage capacity for torpedoes. Notably, the S-80 has been specifically designed as an AIP submarine from the start, providing it with an operational advantage over its Scorpene counterparts. Although the S-80 program has faced complications and delays with the first 2 boats, Isaac Perel, S-81, and Narciso Montreal, S-82, Initially entering service without the AIP system, the subsequent hulls, Cosme Garcia, S83, and Mateo Garcia de los Reyes, S84, will have the AIP incorporated either during construction or through subsequent overhaul. A solemn ceremony took place to decommission the Ekaterinburg, a nuclear-powered strategic missile submarine of Project 667 BDRM. The Project 667 BDRM submarines have a length of 167 meters, a width of 12 meters, and a displacement of approximately 12,000 tons. They can dive to a maximum depth of 400 meters and reach a cruising speed of up to 24 knots underwater. The submarine is crewed by 140 personnel and armed with 16 intercontinental ballistic missiles from the D9 complex. The Ekaterinburg strategic missile submarine, designed by the Central Design Bureau, Rubin, arrived at the Zvezdochka Shipyard earlier than planned due to an emergency incident. Originally, it was scheduled for routine repairs at the Zvezdochka Shipyard in Severodvinsk after its transfer from Gajievo. However, plans had to be adjusted after a fire broke out in the submarine's hydroacoustic station during work at the Nosovaya Gorka ship repair yard in Severomorsk. The fire was complex and intense. Deputy Prime Minister of Russia instructed the Navy and industrial enterprises to quickly restore the damaged ship, taking into account the shortened inter-repair period for Ekaterinburg. To expedite the repair process, the decision was made to combine the emergency repair of the hydroacoustic station and the bow section's hull structures with the planned restoration work. The submarine was brought to the Zvezdochka Shipyard and repair work began immediately, even before the signing of the state contract. A team of specialists inspected the structures and equipment of the damaged first compartment, and Ekaterinburg was lifted out of the water and placed on a solid foundation inside the Zvezdochka dock. Full-scale repair work commenced, and the submarine was later moved to a stable workshop. Between 300 and 600 personnel worked daily on the ship, with the engineering services of Zvezdochka addressing complex tasks and developing technical solutions. Intensive efforts were made to restore the ship's systems damaged by the fire. Collaborative work between Zvezdochka, the Rubin Institute of Marine Technology, and other institutions ensured the preservation, restoration, and continued operation of the ship without limitations. The progress of the repair work was closely monitored by the leadership of the United Shipbuilding Corporation and the Navy's command, with regular progress reports submitted to the Russian government. Eventually, a significant portion of the repair work was completed, and the submarine was ready to be removed from the dock and launched back into the water. Navantia, a renowned Spanish company, is a leader in the field of ship repairs and transformations, especially cruise ships, including large-scale vessels. Its strategic location in the Bay of Cadiz, near the Strait of Gibraltar, makes it an ideal choice for cruise ships operating in the Mediterranean and the Caribbean, as they can conveniently undergo repairs without deviating from their routes. One notable feature is the dock, measuring 386 meters in length, 66 meters in width, and with a draft of 9 meters. This substantial dock capacity can accommodate vessels weighing up to 440,000 tons, ensuring that even the largest cruise ships can be serviced. Four cranes with lifting capacities of up to 100 tons ensure efficient handling during repairs. Additionally, the shipyard has established its own gray and black water treatment plant, capable of processing 500 tons per day, meeting environmental standards. the shipyard's capabilities extend beyond basic repairs. Navantia offers comprehensive turnkey services, including the design, prefabrication, assembly, and testing of various components. Whether it is the installation of propulsion systems such as propellers, stabilizers, and pots, or the completion of painting, interior refurbishment, and the installation of recreational accessories, the shipyard can handle diverse and complex tasks. One of the primary concerns in ship repair is addressing mechanical and electrical system issues. The company possesses the technical know-how and experience to diagnose and rectify problems related to engines, generators, propulsion systems, and various electrical components. Skilled engineers and technicians meticulously analyze the systems, troubleshoot faults, and carry out necessary repairs or replacements. The shipyard's team also specializes in resolving propulsion-related complications. Issues with propellers, thrusters, and steering mechanisms can significantly impact a vessel's maneuverability and performance. The company's experts possess in-depth knowledge of these systems, enabling them to tackle intricate repair tasks such as realigning propeller shafts, refurbishing propellers, and optimizing propulsion efficiency. The shipyard's skilled craftsmen meticulously restore cabins, public spaces, restaurants, theaters, and recreational facilities. From repairing plumbing and electrical fixtures to refurbishing furnishings and finishes, the team ensures that every interior aspect is meticulously attended to, providing passengers with a comfortable and enjoyable experience. We are at the Korkmaz Company's factory based in Turkey. Here we will explore the company's production of high-quality pots, teapots, and household products. Decoiling. Stainless steel sheets are uncoiled to obtain flat sheets, which serve as the raw material for pot production. Stamping and cutting. The flat stainless steel sheets are stamped and cut into specific shapes and sizes, determining the dimensions of the pot bodies. Forming. The stamped stainless steel sheets undergo a forming process, such as deep drawing or pressing, to shape them into pot bodies with rounded sides and a bottom. With modern machines and self-contained production lines, Korkmaz can produce 7,000 pots per day and 3,000 teapots per day. Heat treatment. The formed pot bodies undergo heat treatment to enhance their strength, hardness, and resistance to deformation. Heat treatment involves controlled heating and cooling processes. Inner grinding. The interior surfaces of the pot bodies are precision ground to remove rough edges and imperfections, ensuring a smooth and even inner surface. External grinding. Similarly, the external surfaces of the pot bodies are ground to achieve a uniform appearance and eliminate irregularities. Polishing. After grinding, the pot bodies undergo a polishing step to achieve a smooth and shiny finish, enhancing their aesthetic appeal. Korkmaz utilizes a significant number of automated robots in its production line, which plays a crucial role in streamlining and enhancing the efficiency of their manufacturing processes. These robots are designed to perform various tasks with precision and speed, contributing to improved productivity and quality control. Hole stamping. Holes or perforations may be stamped into the pot bodies for the insertion of handles or other accessories. Handle welding. The handles, typically made of stainless steel or other suitable materials, are welded onto the pot bodies using appropriate welding techniques, ensuring secure attachment and durability. Grinding and polishing. After the handles are welded, the areas around the welds undergo further grinding and polishing to smoothen the surfaces and achieve a seamless appearance. Safety and ergonomics. Robots contribute to improved workplace safety by taking over repetitive, physically demanding tasks that may pose risks to human workers. By automating these tasks, Korkmaz helps reduce the likelihood of work-related injuries and allows employees to focus on more complex and value-added activities. The use of automated robots in Korkmaz's production line enables increased efficiency, consistency, and scalability. By combining the precision and speed of robots with human expertise, Korkmaz can optimize their manufacturing processes and deliver high-quality products to meet customer demands. Throughout the manufacturing process, Korkmaz implements stringent quality control measures to ensure that each pot meets the desired standards in terms of functionality, appearance, and safety. Inspections and tests are likely conducted at various stages to maintain consistent quality. This is AR530, a new section bending machine manufactured by MG SRL, Italy. The AR530 is the biggest section bending machine ever built. It is a giant 29.5 by 29.5, almost 26 feet high, 340 tons, 220 HP with 1900-ton torque. The tube's 610 mm diameter by 22 mm thickness is carefully positioned and secured between the hydraulic side guides. These guides have a tri-dimensional movement, allowing them to adapt to the tube's shape and size. The AR530 features 3 double pre-bending motorized rolls that can accommodate dies up to 43 inches in diameter. These rolls are keyed to 21-inch diameter shafts and are capable of applying substantial force to the workpiece. The hydraulic system is activated, supplying power to various components of the machine. Hydraulic cylinders are responsible for controlling the movement of the bending rolls, minimizing friction, and acting as an anti-deflection system. The bending rolls, driven by hydraulic cylinders, adopt a planetary movement. The vertical section bending (VSB3) machine, developed and produced by Swebend, is an innovative solution for bending angle-shaped beams. With a range of 400 to 3,200 millimeters, this machine showcases cutting-edge technologies and advancements in the field. One notable feature of the VSB3 is its variable center distance between the two lower bending axes. This flexibility allows for precise control over the bending process, accommodating different beam sizes and requirements. Additionally, the pulling unit for rolling beams on the XX axis is seamlessly integrated into the central bending roll console, streamlining the bending operation. The significant advantage of the VSB3 is its interchangeability of shafts across all three axes. This means that customers who already possess their own tooling can utilize it on the new machine, reducing costs and maximizing efficiency. Furthermore, the bending roll shafts are supported at the top while still allowing for rapid tooling adjustment, a breakthrough in the bending industry. This addresses a long-standing challenge and opens up new possibilities for enhanced productivity. The VSB3 also boasts massively proportioned guide rolls, which are integrated with the lower roll shaft housings. This integration ensures optimal positioning during bending, minimizing material waste, and resulting in substantial long-term savings. To enhance user experience, the VSB3 is equipped with an operator-friendly portable wireless control unit. This Bluetooth-enabled device enables seamless control of all machine functions, including digital readouts, providing convenience and efficiency during operation. The process of plate rolling involves feeding a flat metal plate through a series of rollers that apply pressure to the material, causing it to bend and form into the desired shape. Hot rolled plates refer to metal plates that have been heated and formed through the hot rolling process, which involves passing the material through rollers at an elevated temperature to improve its malleability and reduce its thickness. The innovative robotic system developed by Aceta for Cotterman, the manufacturer of rolling metal ladders, is designed to centralize the manufacturing of ladder parts and optimize the production process. The system incorporates 3 FANUC robotic arms, each performing specific tasks to automate the various stages of ladder production, including bending, welding, and palletizing. This automation enables the system to operate continuously, 24 hours a day, 7 days a week. The workflow of the robotic system begins with the bending process. One of the robotic arms, referred to as bend, is responsible for bending the metal components to the desired shape for ladder treads. This arm is equipped with specialized tools and programming to accurately and precisely bend the metal according to the specific ladder design. Once the bending process is complete, the ladder treads move to the next stage, which is welding. Another robotic arm, known as weld, takes over and performs the welding operations on the treads. This arm is designed to handle the welding equipment and execute the welding process with high precision and efficiency. It follows the programmed welding patterns to ensure consistent and reliable welds on the ladder treads. After the welding process, the finished ladder treads need to be palletized for storage and transportation. The third robotic arm, called palletize, takes on this task. It carefully picks up the welded ladder treads and arranges them onto pallets in an organized manner. This palletizing process ensures that the ladder parts are stacked efficiently and securely for easy handling and shipping. By automating these processes, the robotic system offers several advantages to Coderman. First, it reduces the need for manual labor, streamlining the manufacturing process and minimizing the reliance on human workers. This automation also improves the overall turnaround time for ladder production, allowing for faster order fulfillment and increased productivity. Furthermore, the robotic system helps optimize floor space utilization. By centralizing the manufacturing of ladder parts in one plant, Coderman can eliminate the need for multiple production facilities, thus saving on space and operational costs. Additionally, the centralized manufacturing approach facilitated by the robotic system enables Coderman to reduce shipping costs. With all ladder parts produced in one location, transportation logistics are simplified, leading to more efficient and cost-effective shipping.
Ilsenberger Groblik GmbH, operating under the Salzgitter AG conglomerate, stands as a trailblazer in the production of steel plates, distinguished by exceptional quality, diverse applications, and a storied tradition in heavy plate manufacturing. The intricate manufacturing process takes its origins from the Salzgitter steelworks, the primary source of raw materials for Ilsenberger Groblik. This steelworks, the largest and most vital contributor, annually produces a staggering 4 million tons of steel. This relentless production operates year-round, every single day. The journey commences with the creation of pig iron through the operation of 3 blast furnaces. This pig iron undergoes a metamorphic transformation to become raw steel, which is then transported to the Taupo pans in the Angelifert stahlwork. The subsequent oxidation process, achieved by injecting oxygen, is crucial. It purges impurities, facilitating the conversion of pig iron into raw steel. This transformation is followed by a secondary metallurgy stage, where diverse treatments are employed to fine-tune the raw steel's properties. Through regulation, heating, and vacuum processes, the steel attains its desired properties and temperatures. The manufacturing facility boasts 3 state-of-the-art continuous casting plants, capable of transforming liquid steel into solid steel slab. The process initiates with thorough inspection. Upon arrival from Salzgitter, the steel slabs undergo meticulous visual scrutiny. Once cleared, they are integrated into the production process and transported to the furnaces through clinker forks. Laser-based dimensional control and weight measurements ensue, ensuring precision. Subsequently, these slabs are conveyed into the furnaces, where they undergo a heating process lasting approximately 4 hours. The ensuing phase, commonly referred to as the rolling process, is pivotal. This critical operation is fundamental to transforming heated steel slabs into precisely dimensioned plates, ready for a wide range of industrial applications. The process takes place within the confines of the Quarto mill, where meticulous control and advanced technology converge to shape the future of these steel slabs. At the heart of the rolling process is the Quarto mill, a specialized facility designed for the controlled reduction of steel slab thickness and the refinement of its dimensions. This is a complex and precise operation that requires a combination of sophisticated machinery, engineering expertise, and cutting-edge automation. The steel slabs, which have been heated to the appropriate temperature, are carefully introduced into the Quarto mill. These slabs are massive in size and carry immense potential in their transformation. The process involves guiding these steel slabs through the gap between two working rolls. These rolls play a vital role in exerting pressure and shaping the steel slabs, leading to the reduction in thickness and the refinement of their overall dimensions. Advanced spindle systems are the backbone of this rolling operation. These systems consist of robust motors that drive the movement of the rolls. Their precision and power are crucial to maintaining control over the process, ensuring that the transformation is executed flawlessly. The movement of the rolls is meticulously orchestrated, allowing for precise control over the reduction of thickness and the shaping of the steel. A cornerstone of this process is the self-developed rolling schedule calculation model. This model acts as a guiding force, dictating the parameters and controls that need to be applied to the rolling operation. It takes into account a plethora of factors, such as slab temperature, desired plate thickness, width, length, and even the properties of the steel being used. This model is a result of years of research, data collection, and engineering finesse. It ensures that each plate is rolled with the utmost precision and adherence to specific tolerances, resulting in plates that meet the exact requirements of the customers. Post-rolling, the plates undergo an array of treatments, including cold straightening and heat treatment, designed to bring forth the desired mechanical and technological properties. The water-intensive cooling process plays an integral role. Additionally, the plates might be subjected to hot marking, warm stamping, and other processes, all orchestrated to meet the specific requirements of customers. The culmination of the process entails cutting, surface preservation, meticulous quality control, and packaging for shipment. Plates are subjected to a rigorous inspection, which includes assessments for surface defects and internal imperfections through methods such as ultrasonic testing. Mechanical properties are rigorously tested through a suite of procedures, encompassing pendulum impact testing and hardness measurements. Monopiles are large cylindrical structures that serve as the foundation for offshore wind turbines, supporting the weight of the entire turbine and transmitting the forces generated by wind and waves into the seabed. The production process begins with plate delivery. High-quality steel plates, chosen for their durability and strength, are transported to the manufacturing site. Rolling and tack welding come next, where the steel plates are formed into cylindrical shapes through precise rolling techniques. Tack welding, a preliminary welding process, holds the structure temporarily together for further assembly. The monopile's longitudinal welding phase follows, involving both internal longitudinal welding and external milling. Internal longitudinal welding joins the individual plate edges within the structure, creating a seamless interior. External milling ensures the smoothness of the exterior surface, optimizing the weld quality. Subsequently, the monopile's transport to its installation site is carried out. This often includes transporting sections, cans, and cones to designated locations. Upon arrival at the installation site, positioning, tack welding, and circumferential welding occur. Tack welding secures the monopile in place temporarily, after which internal and external circumferential welding is conducted. These welding procedures are meticulously executed to ensure the structural stability and integrity of the monopile. To ensure the quality of the welds and positioning, rigorous testing processes are undertaken. Ultrasonic testing of welding detects any potential flaws within the welded seams. After successful testing, the monopile undergoes a coating process in a specialized coating hall. This involves multiple steps such as in and outside washing, blasting, metallization, and coating.
The manufacturing process of rotor blades involves a meticulous series of steps to create durable and efficient components for wind turbines. Rigorous testing and careful construction are paramount to ensure these blades endure the harshest forces of nature over their life cycle. The process begins with extensive static and fatigue tests, which simulate the blade's exposure to environmental stresses. Lightning strike tests and aerodynamic evaluations are also conducted at LM Wind Power's dedicated wind tunnel to ensure the blade's robustness. The blade's core construction includes laying glass fiber layers, providing a foundation for the composite material. To enhance strength and stability, balsa wood panels or PET foam are strategically placed within the blade. In longer blades, carbon fiber reinforcement is integrated to improve stiffness. Precision measurements are meticulously adhered to during the assembly to meet the required tolerances. Dry fabrics are infused with resin to form a composite laminate, enhancing the blade's structural integrity. A shear web is introduced between two shells and glue is carefully applied. The two shells are then joined, forming the blade's distinctive shape. The finishing process is exhaustive, ensuring the highest quality standards are met. Each blade undergoes meticulous inspections and adjustments, ensuring that it performs optimally once installed. With the manufacturing completed, the finished rotor blade embarks on its journey to its final destination. It becomes a vital component in harnessing wind energy. With a vision to contribute to a greener future, Nordex has set ambitious goals, including providing fully recyclable turbine blades by 2032 and reducing the carbon footprint of its turbines by 25% by 2025. This dedication to environmental responsibility has yielded significant results, with approximately 60 million tons of Colorado II emissions saved worldwide in 2022 alone due to the implementation of Nordex turbines. The manufacturing process of Nordex turbines is guided by a comprehensive approach that considers economic, ecological, social, and health and safety-related aspects. This approach encompasses all stages, from design and construction to installation, service, and the end-of-life phases. This commitment to circularity is especially evident in the Delta 4000 turbine, designed for the global market. The turbine's modular components and harmonized design facilitate material handling, stock keeping, and service across various production sites worldwide, enhancing efficiency and sustainability. While wind turbine materials are already highly recyclable, Nordex is focusing on further improving the recyclability of composite materials used in rotor blades. These efforts align with the company's dedication to minimizing its carbon footprint. Nordex's Cost of Energy Co-program is another key initiative aimed at reducing electricity generation costs. This program employs strategies such as increasing yield and extending service life while optimizing resource utilization and logistics concepts. By incorporating innovations such as self-hoisting crane solutions, the company minimizes turbine downtime and enhances yields, thereby reducing the overall environmental impact of its turbines. The Life Cycle Assessment (LCA) report for Nordex's Delta 4000 turbines underscores the company's eco-conscious efforts. It reveals that the specific carbon footprint for producing 1 kilowatt-hour of electricity over the turbine's entire life cycle is impressively low at 2.7 G, Colorado 2E. The material composition of Nordex turbines, such as the N149/0.0 to 4.5 TS105 model, highlights the dominance of steel at 87% of the material mix. Glass fiber and carbon fiber reinforced composites account for 9%, while plastics contribute 1.5%. Other materials, including operating fluids, electronics, aluminum, and copper, make up the remaining 2.4%. The installation process of a wind turbine commences with excavation, a monumental task that requires a substantial area to be cleared. A space measuring 100 feet in width and excavated to a depth of 10 feet provides the foundation for the turbine. This excavation is more than just digging a hole. It's about preparing a solid base that can withstand the immense forces and loads that the turbine will experience throughout its lifetime. The reinforcement of the foundation comes next. Reinforcing steel, weighing up to an astonishing 96,000 pounds, is carefully positioned within the excavation to provide the necessary structural support. The pouring of concrete marks a pivotal stage in the installation process. To create a solid foundation, 53 concrete trucks are mobilized to pour an impressive 1,500 cubic yards of concrete into the excavated area. The rotor blades, each an impressive 173 feet in length and weighing a substantial 27,000 pounds, are transported to the site. This is no ordinary transportation. 8 truckloads are required to deliver all the necessary components. The nacelle, a massive structure comparable in size to a school bus, houses the turbine's critical components. Within its confines are the generator, gearbox, and rotor shaft, elements essential for the conversion of wind energy into electricity. Speaking of the tower, the assembly of its sections is a meticulous operation. The base tower, standing at a height of 53 feet and 11 inches, weighs a substantial 97,459 pounds. Supported by a staggering 160 bolts around its base, the tower's stability is paramount to the safety and effectiveness of the turbine. The mid-tower section follows, reaching a height of 84 feet and 6 inches and weighing 115,587 pounds. The assembly of these tower sections demands careful coordination and engineering expertise, taking an average of 5 hours to complete. The rotor assembly, which includes the hub and the massive blades, is yet another critical step. With a diameter spanning 354 feet, the rotor assembly is a marvel of modern engineering. The intricate process of assembling the rotor takes approximately 4 hours, as technicians work diligently to ensure its seamless integration with the rest of the turbine structure. As the top tower section, measuring 119 feet in height and weighing 104,167 pounds, is assembled, the turbine nears its final form. The completion of the turbine structure signifies the moment when it's ready for operation. The nacelles installation is a delicate procedure, as it weighs a staggering 181,000 pounds. This process involves meticulous preparation and strategic lifting to ensure that the nacelle is securely and accurately positioned at the top of the tower. With its towering height of 442 feet from the base to the blade tip, the turbine stands as a testament to human ingenuity and dedication to harnessing renewable energy sources. In the end, the entire installation process, from excavation to operation, takes approximately 3 weeks to accomplish. This timeline encapsulates the meticulous planning, technical precision, and coordinated effort required to bring a wind turbine to life. As the turbine's rotor blades capture the kinetic energy of the wind and convert it into electricity, the result is a clean, sustainable, and environmentally friendly energy solution that contributes to a greener future for generations to come.
We are at the Czech-based Skrukovice roller casting division specializes in the production of working rollers for hot rolling mills. They employ centrifugal casting technology using licensed Gonterman Pipers technology. Annual production is between 6,000 and 7,000 tons of rolls. The working layer of the rolls is made from a variety of materials, including high chromium cast iron, indeterminate hardened cast iron, tool steel, high-speed steel, and ductile iron. To expand their capabilities, a new production hall has been constructed for the production of centrifugally cast castings weighing up to 300 kilograms. This centrifugal casting technology is particularly suited for achieving high material homogeneity. The Roller Foundry division mainly focuses on the production of cylinders through gravity casting in coxicles and sand, with weights ranging from 5,000 to 8,000 kilograms. Additionally, they undertake piece and small series production of shaped castings in gray iron, ductile iron, and steel, weighing between 40 and 15,000 kilograms. The division also handles gravity and centrifugal castings of non-ferrous metals, ranging from 5 kilograms to 4,000 kilograms. These cylinders have dimensions ranging from a minimum of 500 millimeters diameter and 1,050 millimeters length, up to a maximum of 6,000 millimeters length and weight between 4 and 22 tons per piece. Meraviglia, Italy is a leading production facility renowned for its excellence in forging and metalworking processes. The production facility boasts 13 furnaces, each with a maximum capacity of 400 tons. These furnaces enable Meraviglia to handle large-scale projects efficiently. The forgings produced at Meraviglia can reach impressive dimensions, with a maximum length of 23 meters, diameter of 8,500 millimeters, and weight of 250 tons. Such capabilities make Meraviglia well-equipped to tackle complex and demanding forging tasks. Meraviglia employs a rail-bound manipulator with a remarkable load capacity of 300 tons. This equipment enables the precise handling and transportation of heavy forgings within the facility. Additionally, the integration of a hydraulic forging machine with a capacity of 16,000 tons ensures efficient forging processes. Meraviglia's perfect interaction between press and ring mill guarantees optimal results. The facility specializes in producing rolled rings measuring 8,000 millimeters by 4,000 millimeters, with a weight of up to 150,000 kilograms. With an annual production capacity of 75,000 tons, Meraviglia meets the demands of various industries that require reliable and high-performance forged components. Merendina's production capabilities extend beyond forgings to include a diverse range of products such as shafts, flange shafts, mandrel bushes, blocks, plates, and bushes. The facility also incorporates ultra-low emission regenerative burners, which not only ensure environmental sustainability but also enhance energy efficiency during the forging processes. The production facility houses a state-of-the-art radial axial hot rolling plant, which is recognized as one of the most powerful worldwide. To support the production processes, they maintains a range of cutting-edge machinery. This includes 22-band sawing machines with a maximum diameter of 3,000 millimeters. The ServoMaster 3200 is a highly advanced press manufactured by Zani Spa Metal Forming Machines, an Italian company with a rich history in designing and producing presses for sheet metal forming. Founded in 1960 by Giovanni Zaffaroni, Zani has evolved over the years to become a prominent player in the international market, offering a wide range of products from 200 tons to 3,200 tons with bolsters up to 7 meters in length. The manufacturing process of the ServoMaster 3200 involves a collaborative approach, starting with the design phase conducted by the research and development engineers of the company's technical office. These engineers work in close collaboration with the Milan Polytechnic, which performs structural calculations to ensure the press's integrity and reliability. The production of the press is a combination of in-house manufacturing and the involvement of qualified external suppliers. Zani utilizes its internal resources for production, while certain processes such as heavy carpentry, boring and milling, and gear toothing are outsourced to trusted suppliers. This approach ensures that each component of the press meets the highest quality standards. The high performance of the ServoMaster 3200 is achieved through the integration of servo technology and lever kinematics, which have been developed by Zani over the years. These advancements enable precise control and efficient operation of the press. Additionally, the press features a unique solution for changing molds, ensuring strength, dimensional accuracy, precise coining, and optimization of the production cycle. These factors contribute to making the ServoMaster 3200 one of the most significant presses in Europe today. The company takes pride in its ability to cater to diverse customer requirements. Each press is designed and manufactured according to the specific needs of the customer. With a wide range of presses available, including eccentric presses, link motion presses, servo presses, and presses for lamination, they offer solutions for various production needs across industries such as automotive, appliances, electronics, furniture, and renewable energies. Doosan, a leading industrial conglomerate, recently celebrated the installation of its groundbreaking 17,000-ton forging press at the forging plant of its manufacturing complex in South Korea. This colossal press is now the world's largest and represents a significant milestone in the field of metalworking. Located at the heart of the forging plant, this impressive machinery is responsible for shaping steel ingots into specific forms through immense pressure. Standing tall at 29 meters and measuring 9 meters wide, the 17,000-ton forging press possesses an astonishing capability to exert force equivalent to that of 240,000 individuals simultaneously applying pressure on the metal. Remarkably, it currently holds the title of being the world's largest four-pillar type forging press. With the integration of this state-of-the-art forging press, Doosan's manufacturing complex has significantly increased its production capacity. The forging plant now has the ability to manufacture an astounding 80,000 tons of forged materials annually. To put this into perspective, This weight is equivalent to approximately 50,000 mid-sized sedans, showcasing the substantial scale and impact of this new technology. To forge a round bar, the forging press, manipulator, and ingot bogie work together in a coordinated process. The ingot bogie transports a large metal ingot to the forging press. The ingot is preheated to make it more malleable. The manipulator grips the heated ingot securely and positions it in the die assembly of the forging press. The manipulator ensures precise alignment for optimal forging. The forging press is activated, generating immense hydraulic force. The press applies pressure to the ingot, compressing it between the upper and lower dies. The high pressure force deforms the ingot, causing it to elongate and take on the shape of the die. As the ingot is compressed, it transforms into a round bar with the desired dimensions. The manufacturing process of steel bars at Scott Forge Bar Mill in Clinton, Wisconsin involves a combination of forging, rolling, and machining techniques. They offer a range of forged and rolled bars with diameters ranging from 6 inches to 16 inches and lengths up to 40 feet. For larger bars, they utilize open die presses. Depending on the customer's requirements, the bars can also be machined or peeled. Tartan bars, specifically, undergo a preliminary forging process to consolidate the centers. Subsequently, a planishing operation is performed, where the bars are passed through a set of rollers multiple times. This planishing process imparts a rolled surface to the bars while ensuring sound centers, with a minimum reduction ratio of 3:1. The rolled ring forging process is a specialized metalworking technique used to manufacture seamless rings of varying sizes and materials. The process begins with a circular metal blank. The blank is heated to a specific temperature to improve its formability. Once heated, the blank is placed on a mandrel or an inner core. A rolling machine exerts tremendous pressure on the blank while simultaneously rotating it. This combination of pressure and rotation causes the blank to deform and take the shape of the mandrel, gradually forming a hollow ring. The rolling process ensures a controlled flow of material, resulting in a uniform grain structure and excellent mechanical properties. It eliminates the need for welding or joining operations, creating a seamless and defect-free ring with enhanced strength and structural integrity. The CDRA hydraulic press, specifically the CDRA 500Z DOS model, is a specialized machine used for the adjustment of railway wheel sets. It employs cold pressing techniques without the need for guide bushings, allowing for efficient and precise production of railway wheel sets. The press is equipped with axle turning capabilities and enables the pressing of parts between the wheels, offering versatility in its functionality. The design of the CDRA hydraulic press features a horizontal layout with a columnar construction, ensuring stability and durability during operation. The press cylinder, positioned in the stationary crossbeam, exerts force on the pressed components against the bearing crossbeam. This arrangement allows for effective and controlled pressing operations. The movement of the crossbeam is facilitated by threaded anchors that provide preset measured positions. This ensures accurate and repeatable positioning of the pressed components, enhancing the quality and consistency of the produced railway wheel sets. The supporting crossbeam is equipped with hydraulic wheel centering, which aids in aligning the wheels correctly during the pressing process. Additionally, the rear crossbeam features hydraulic axle centering, further enhancing the precision and alignment of the wheel sets. A sophisticated control system is integrated into the CDRA hydraulic press, providing comprehensive control over the machine's operation. It enables operators to initiate and monitor pressing operations, conduct diagnostics of the pressing process, and identify any errors or deviations. This control system enhances productivity, efficiency, and safety during the adjustment of railway wheel sets. The CDRA 500Z DOS model of the CDRA hydraulic press is specifically designed to meet the requirements of railway wheel set adjustment. It offers a robust and reliable solution for pressing on, pressing off, and checking fittings. With its advanced features and precise control system, the CDRA 500Z DOS ensures that the adjustment process is carried out with accuracy and efficiency.
This dishead manufacturing process involves cutting, welding, pressing, and flanging steel plates to create a component with a 3,650 mm diameter and a thickness of 12 mm. The 12 mm thickness steel plates are cut into 3,650 mm diameter circular plates. For those of insufficient size, they will be welded together. During the pressing operation, the welded or single piece of steel plate is placed between the dies of a hydraulic press. The hydraulic press is equipped with a ram that applies high pressure to the material. As the press activates, the ram moves downward, exerting tremendous force on the material, which causes it to deform and take on the desired shape. The pressure applied by the hydraulic press is carefully controlled to ensure precise shaping while avoiding excessive deformation or damage to the material. In the flanging process, specialized machinery are utilized to create a rim or edge along the periphery of the dishead component. The process starts with positioning the component within a flanging machine. The flanging tool, which consists of a die and a punch, is then brought into contact with the material. The punch applies force to the material, while the die provides support and shape to the flange. The force exerted by the punch causes the material to deform and bend, resulting in the formation of the flange. This process helps increase the strength and rigidity of the component, as well as provide a defined shape and an edge that can be used for joining purposes. This is a versatile and efficient tool designed to simplify and streamline the process of creating elbows using Phi 120 pipes. With this innovative machine, the operator can effortlessly bend and shape Phi 120 pipes into precise and accurate angles, ensuring a perfect fit for your plumbing construction. The machine is specifically designed for Phi 120 pipes, which have a diameter of 120 millimeters. This size is commonly used in various applications, such as industrial piping systems, water supply lines, or HVAC installations. This machine operates manually, requiring the user to provide the necessary force to bend the pipes. A lever mechanism allows the operator to control the bending process with precision, ensuring consistent results. The machine offers adjustable angle settings to accommodate different bending requirements. Operator can easily set the desired angle for the elbow, ranging from 0 to 180 degrees, using clear and intuitive controls. The guillotine cutter is a hydraulic metal cutting machine designed to process materials of different thicknesses. In this case, a steel plate with a thickness of 25 millimeters. It operates based on a shearing mechanism. The process starts by positioning the metal sheet to be cut on the machine's work table. The operator sets the desired cutting length and adjusts the back gauge accordingly. Once the material is properly aligned, the hydraulic system activates, powering the downward movement of the guillotine blade. As the blade descends, it applies a powerful force onto the metal sheet, exerting enough pressure to separate the material along the desired cutting line. The sharp blade slices through the metal, producing a clean and precise cut. This section shows how heavy-duty press brake forming work. Real steel used nearly all 1000 T of pressing force on this 6 meters piece of 16 millimeter steel on the biggest press brake in New Zealand. Heavy-duty press brake forming is commonly employed in industries such as construction, shipbuilding, automotive, and manufacturing, where the fabrication of large and sturdy components is required. The process involves clamping the workpiece between a punch and a die and applying significant force to deform the material into the desired shape. The advanced capabilities of heavy-duty press brakes enable the bending of thick and rigid materials with precision and efficiency, allowing for the creation of complex and durable metal components for various applications. The 58 feet by 2200T Accurl USA tandem press brake is a powerful machine designed for bending large format poles with precision and efficiency. This press brake utilizes advanced hydraulic systems and computer-controlled technology to perform its bending operations. The process begins by loading the steel plate onto the press brake's work surface. The operator inputs the desired bending parameters and specifications into the control panel. The machine's hydraulic cylinders exert immense force, pressing the steel plate against a series of precision tooling. As the hydraulic cylinders apply pressure, the steel plate is gradually bent into the desired shape. The operator closely monitors the bending process through the control panel, ensuring that the correct angles and dimensions are achieved. The machine's robust frame and tandem configuration provide stability and allow for the bending of longer poles without sacrificing accuracy. The cut-to-length line with special saw by Kohler operates through a series of well-coordinated steps, combining advanced technology and precision engineering to deliver accurate and efficient metal cutting processes. This section shows an overview of how this equipment works. Material loading. The process begins with loading metal coils or sheets onto the cut-to-length line. The material is fed into the line, either manually or through an automated feeding system, depending on the configuration and requirements of the specific setup. Straightening and leveling. The metal material passes through straightening rolls and leveling devices. These components remove any residual coil set or waviness in the material, ensuring a flat and uniform surface for accurate cutting. Measurement and positioning. The line incorporates sensors and measurement systems that precisely determine the length of the metal material. These measurements are communicated to the control system, which calculates the required cut length and positions the material accordingly. Clamping and fixation. Once the material is in position, clamping mechanisms secure it firmly to prevent any movement during the cutting process. This ensures stability and accuracy in the cutting operation. Cutting operation. The special saw, designed specifically for this cut-to-length line, is activated to perform the cutting process. The saw blade moves across the width of the material, applying a precise cutting action to sever it at the predetermined length. The saw blade's speed and feed rate can be adjusted to accommodate different metal types and thicknesses. Scrap removal. After the cut is made, any scrap or excess material remaining is removed from the line. This can be achieved through various methods, such as a conveyor system or pneumatic ejection devices, depending on the equipment's design. Unloading and stacking. Once the cut material is separated from the scrap, it is unloaded from the line and either stacked or further processed as required. The line may incorporate stacking systems, robotic arms, or conveyor belts to facilitate efficient material handling and organization. Throughout the process, the cut-to-length line with special saw is controlled by a sophisticated control system. This system oversees the entire operation, integrating the measurements, positioning, cutting parameters, and other variables to ensure accuracy, consistency, and efficiency. It also provides operators with user-friendly interfaces and real-time feedback, allowing for easy monitoring and adjustment of the cutting process. The WFL M200 mill turn is a high-end multitasking machining center used for complex milling and turning operations. This machine is capable of producing complex parts in a single setup, which can reduce cycle times and improve part accuracy. The M200 mill turn is designed to handle a wide range of materials including aluminum, steel, titanium, and more. One of the standout features of the M200 mill turn is its versatility. It can perform a range of machining operations including drilling, milling, turning, and tapping. Additionally, the machine has the ability to perform 5-axis machining, which allows for more complex geometries to be machined. Another key feature of the M200 Miltern is its precision. The machine is equipped with high-accuracy linear scales and rotary encoders to ensure precise positioning of the workpiece. It also features a hydrostatic guideway system which provides a high level of stiffness and damping, resulting in improved surface finishes and reduced tool wear. The M200 Miltern is controlled by a Siemens 840D SL CNC system, which provides users with a high degree of flexibility and control over the machining process. The machine is also equipped with a range of sensors and monitoring systems to ensure safe and efficient operation. The WFL M120 Miltern is a state-of-the-art machining center that offers high precision and versatility in completing complex aerospace parts. In the aerospace industry, where every component must be manufactured to exacting standards and specifications, the M120 Miltern provides an ideal solution for producing high-quality parts with high accuracy and repeatability. The M120 Miltern is a multi-axis machine that combines the capabilities of a lathe and a milling machine. It has a maximum turning diameter of 240 millimeters and a maximum turning length of 1,300 millimeters, making it suitable for a wide range of aerospace parts. The machine has a C-axis and a B-axis that allow for simultaneous milling and turning operations, which is critical in producing complex parts that require multiple machining operations. One of the key features of the M120 Miltern is its high level of automation. The machine is equipped with a tool changer that can hold up to 120 tools, which allows for uninterrupted machining operations without the need for manual tool changes. Additionally, the machine has a pallet changer that enables the operator to load and unload parts while the machine is still in operation, reducing downtime and increasing productivity. Another important feature of the M120 Miltern is its high level of accuracy. The machine is equipped with linear motors that provide fast and precise movement, and a Heidenhain linear scale that ensures accurate positioning. The machine is also equipped with a Renishaw touch probe that allows for accurate measurement and alignment of parts, ensuring that every component meets the exacting tolerances required in the aerospace industry. The M120 Miltern is also designed for easy programming and setup. The machine is equipped with a Siemens 840D SL control system that allows for easy programming and monitoring of machining operations. The system provides real-time feedback on machining performance, allowing the operator to make adjustments on the fly to ensure optimal machining results. Additionally, the machine has a user-friendly interface that makes it easy for operators to set up and run the machine, reducing the need for extensive training and increasing productivity. When used to complete aerospace parts, the M120 Miltern offers several advantages. For one, its ability to perform multiple machining operations in a single setup reduces the number of setups required, which saves time and reduces the risk of errors. Additionally, the machine's high level of accuracy ensures that every part meets the exacting standards required in the aerospace industry, reducing the risk of component failure and increasing safety. The M120 Miltern can be used to manufacture a wide range of aerospace parts, including engine components, landing gear parts, and structural components. For example, the machine can be used to produce engine shafts, which require precise turning and milling operations to ensure proper alignment and balance. The machine can also be used to produce landing gear components, which require high strength and durability to withstand the stresses of landing and takeoff. Additionally, the machine can be used to produce structural components, such as wing spars and fuselage frames, which require high accuracy and repeatability to ensure proper fit and function. Compressors are mechanical devices that are used to increase the pressure of a gas by reducing its volume. They are used in a variety of applications, such as refrigeration, air conditioning, and industrial processes. Walton is the first and only compressor manufacturing company in Bangladesh. The company follows a well-defined manufacturing process for producing compressors. The manufacturing process of a compressor starts with the crankcase line. The casted crankcase is loaded as raw material on the line. The crankshaft line follows where the casted part is taken as input to the machining line. In the pre-machining unit, rough operations such as turning, drilling, and milling are performed. The flange bearing line follows the same process as the crankcase and crankshaft line. Casted flange bearing is loaded as raw material on the line. In the piston line, sintered piston is loaded as input. First, rough grinding operation is done with a centerless grinding machine. Then sandblasting is done to get a smooth surface. The connecting rod line follows where the lamination press line produces laminated sheets for the stator. These sheets are taken at definite sizes as per design, and the insulation layers are inserted. After that, the winding wires are inserted as per design. Then the stator is sent to the next stage where lacing is done. Finally, the finished stator is sent to the next station rotor die casting line. Here, the stator is placed inside the mold where the molten aluminum is poured. After that, the die-casted rotor is taken out from the mold and sent to the next station deep drawing line stamping line. The stator is a stationary part of the compressor that houses the winding wires, which generate the magnetic field required for the compressor to function. In the winding stator station, the stator is assembled by inserting insulation layers between the laminated sheets. The winding wires are then inserted as per the design of the compressor. The winding wires are wound around the laminated sheets, and their configuration is critical for the compressor's performance. The winding wires are typically made of copper and have a coating of insulation material to prevent short circuits. The first step in the shell welding line is to prepare the accessories and mountings that will be welded to the lower shell. These include foot straps, hermetic terminals, terminal fences, steel pins, and tiers. These components are carefully inspected to ensure that they meet the required specifications before they are loaded onto the welding line. Once the accessories and mountings are ready, the lower shell is placed on the welding line. The components are then welded to the shell using high-quality welding equipment. The welding process is carefully monitored to ensure that the welds are strong and that there are no defects in the welds. After the welding operation, the assembled shells are sent to the internal assembly line. This is where all the internal components of the compressor are assembled. The components are carefully inspected to ensure that they meet the required specifications before they are loaded onto the assembly line. The components that are assembled on the internal assembly line include the stator, rotor, crankshaft, connecting rod, piston, valve plate, and other internal components. The components are assembled in a specific sequence to ensure that the compressor functions properly. In the external line, the upper shell is placed in a spur position and welded with the lower shelf. After welding, the rubber plugs are inserted, and finally, the hermetically sealed compressor is sent for painting. The finishing line is the final station of compressor production, where the compressor is filled with oil depending on the Phrygian time and model. After labeling, barcode sticker, and electrical safety test, the compressors are palletized for transportation and storage. Hairpin bending is a process used in the manufacturing of electric motors, generators, and compressors. It involves bending copper wires into a hairpin shape to form the stator coils. The hairpin-shaped wires are then inserted into the slots of the stator core, which is a part of the motor or compressor that rotates. The hairpin bending process typically involves the use of automated machines that can bend the copper wires with high precision. The machines can handle large volumes of wire, and they can bend the wires into different shapes and sizes to match the requirements of the stator core.